சார் ஹலோ
சார் குட் மார்னிங் சார் கண்ணன் சார்
குட் மார்னிங் குட் மார்னிங்
குட் மார்னிங் சார்
மேடம் இப்போ தான் கேட்டாங்க திரும்பியும் நான் அனுப்பிச்சிருக்கேன் அவங்களுக்கு
ஓ சரிங்க சார்
அவங்க
சரிங்க சார்
லைன்ல வர சொல்லியிருக்கேன்
ஓகே சார் ஓகே சார் ஓகே சார்
உங்க வீடியோ காமிங்க
நான் வரேன் சார் ஒரு ஜஸ்ட் ஃபியூ மினிட்ஸ் சார் 1 மினிட்
இல்ல பரவாயில்ல பேச்சு கேட்குது போதும்
சார் சார்
ஈசியோட முகமும் ரெஜிஸ்டார் முகமும் தெரிஞ்சா போதும்
எஸ் சார்
நம்மளை பத்தி பிரச்சனை இல்லை
சார் எஸ் சார் பேனல்ல இன்னொரு ப்ரோக்ராம் போயிட்டு இருக்கு ப்ரோ சார் அதனால தான் வேற ஒன்றும் இல்லை
ஒன்றும் இல்லை நீங்க இந்த எல்லாத்தையும் ரெக்கார்ட் பண்ணிருங்க சார்
கண்டிப்பா ரெக்கார்ட் ஆகிட்டு இருக்கு சார் இப்போ நீங்க பேசுறது கூட ரெக்கார்ட் ஆகும் நான் உங்களுக்கு அனுப்பும்போது கட் பண்ணிட்டு தான் அனுப்புவேன்
அவ்வளவுதாங்க
எஸ் சார் ஏன்னா எதையும் மிஸ் பண்ண கூடாதுங்கிறதுக்காக நான் ரெக்கார்டிங் ஸ்டார்டிங்
ரெட்ல தான் இருக்கு நான் பார்த்தேன்
அப்படியே யூடியூப்ல பாருங்க ப்ரோ சார் உங்க வரும் ஃபேஸ்
ஆமா இருக்கு 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 இருக்குது
எஸ்
கேஏங்கிறது கண்ணனா கேஏ
எஸ் சார்
ஓகே குட் கண்ணன் ஹைக் HGO info
knowledge applied along with higher goal sir
knowledge
applied along with higher goal cargo
super 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 சரி இப்ப அவங்கள வர சொல்லிருக்கேன்
எஸ் சார் ஓகே
மேடம் HOD வந்தாங்கன்னா
எஸ் சார் ஓகே
அப்பலே போன்ல சொல்லிட்டேன் லிங்க் ஆகலன்னு
சரிங்க சார்
இதுல வச்சுக்கிட்டு அவங்க லைன் கூப்பிடலாமா முடியுமா
ப்ரோ சார்
நான் இத மினிமைஸ் பண்ணிட்டு
நீங்க கூப்பிடுங்க ப்ரோ சார் கூப்பிடலாம் நீங்க சென்டர் பட்டன் இருக்கும் பாருங்க போன்ல
ஆமா ரவுண்ட்
அத கிளிக் பண்ணிட்டு நீங்க எப்பவும் போல உள்ள போயிருங்க
போன் பேசி திரும்ப கட் ஆயிட்டு வரணுமா
திரும்ப கட் பண்ண வேணாம் நீங்க அப்படியே மேல இருக்கும் ஜூம் மீட்டிங்னே இருக்கும் ஜூம் கால்னே
சரி
அத கிளிக் பண்ணீங்கன்னா நீங்க உள்ள வந்துடலாம்
அப்படியே அந்த பாக்குறேன் அவங்கள கூட்டி சொல்லிடுவேன்னு பாக்குறேன்
சொல்லுங்க ப்ரோ சொல்லுங்க
எங்க இருக்கு மேல இருக்குங்க இப்போ லைன் எடுத்து அவங்க கட் பண்ணாங்க பார்க்கலாம்
ஓகே சார் அவங்க ஒரு வேளை கனெக்ட் ஆயிட்டு இருப்பாங்க நீங்க சார்
இருக்கலாம் இல்ல வீசிட்ட பேசுறாங்களா என்னமோ
எஸ் சார்
ரெண்டுல ஒண்ணு இருக்கும்
ஓகே
தமிழ் தகவல் ரெடியா இருக்கா
ரெடியா இருக்கு சார் சார்
வேணும்னா போட்டுலாம் அவங்க கேட்டால்
எஸ் சார் ஷூர் சார்
சாப்பிட்டீங்களா நீங்க
சாப்பிடணும் ப்ரோ சார்
சரி ஆரம்பிச்சு விட்டு சாப்பிட்டுக்கலாம்
எஸ் சார்
நானுமே சாப்பிடல இன்னும்
சார்
விசி ரெஜிஸ்டார் பேசிட்டா அப்புறம் ஒன்றும் பிரச்சனை கிடையாது ஸ்பீக்கர் பேசும்போது நம்ம ரெஸ்ட் எடுத்துக்கலாம் ஒன்றும் குழப்பம் இல்லை லேப்டாப்ல போட்டு பார்க்கவா சார் மற்றவங்க எல்லாம் மோட் பண்ணிருங்க
எல்லாமே மீட் பண்ணிடுவேன் சார்
கன்வீனர் விசி ரெஜிஸ்ட்ரார் விமலா நானு இதெல்லாம் கோஸ்டார்ல போட்டு மற்ற எல்லாரையும் மியூட் பண்ணி வச்சுக்கோங்க
ஷூர் சார்
எடுக்க வேணாம்ல.
Sir, good morning. Soleraj sir, good morning.
Good morning, madam. Good morning. Good morning, madam.
Sir, நான் என்னோட வெல்கம் அட்ரஸ் அவருக்கு அனுப்பி ஷேர் பண்ணட்டுமா இல்ல நானே ஷேர் பண்ணலாமா?
நீங்க பண்ணால் அவர் ஷேர் பண்ணுவாரு, இல்லாட்டா நீங்க முடியும்னா நீங்க பண்ணிக்கோங்க. ஏன்னா இப்போ லாஸ்ட் மினிட் 10 மினிட்ஸ் அவரை குழப்ப வேண்டாம், நம்மளே ஷேர் பண்ணிக்கோங்க மேடம்.
ஓகேங்க சார், ஓகே.
அவர் ரெடியா இருக்காரு. விசி மேடம் 10 மணிக்கு மேல எப்போ வந்தாலும் ரெக்கார்ட் பண்ணிடுவார். இப்போ ரெக்கார்ட் பண்ணிட்டு தான் இருக்கு.
ஓகேங்க சார், ஓகே.
எல்லாமே ரெடியா இருக்கு மேடம், ரெக்கார்டோட கரெக்டா இருக்கு மேடம்.
சார்
எஸ்
சார், நான் ஒரே ஒரு வாட்டி தமிழ் தாய் வாழ்த்து மட்டும் போட்டு டெஸ்ட்
பண்ணிக்கோங்க மேடம்.
சார்
சொல்லுப்பா. யுக்தலட்சுமி, சென்னை. நீங்க செக் பண்ணா பண்ணிருங்க. ஒரு 3 மினிட்ஸ் தானே போட்டு பார்த்துருங்க.
தமிழ் தாய் வாழ்த்து மட்டும் போட்டு.
எஸ் எஸ் எஸ். அதுக்குள்ள விசி வரதுக்குள்ள முடிச்சிருங்க. நியூட்ரல் லக்ஷ்மி சென்னை கரெக்டா இருக்கு.
தேங்க்யூ சார்.
லக்ஷ்மி கரெக்டா இருக்கு. போதும்பா, இவ்வளவு போதும்பா. நோ ப்ராப்ளம்.
ஓகே சார்.
சார் குட் மார்னிங் சார்.
குட் மார்னிங் மேடம்.
சார் ஓகேங்க சார். ஓகே தானே சார்? தமிழ் தாய் வாழ்த்து போதும் இல்ல சார்?
போதும் மேடம், அருமையா இருக்கு. போதும் மேடம்.
தேங்க்யூ சார். தேங்க்யூ சார்.
முக்கியமான நேரத்துல நெட் இருக்கு. சார்ஜ் கம்மியா இருக்கு. அதுக்கு இதுதானோ, அதுவும் இது இடம் தானே. வராதா? ஏழரைக்கே அடிக்காங்க. யார் அடிச்சா? மேடம் தான் அடிச்சா. 50% இருக்கு. 1 hour தான் பிடிங்கி விட்டுருவா. 1 hour தான்.
கரெக்டா working days வருது. இந்த இடையில பிரேக் பண்ணாம விட்டா
கண்ணன் சார்.
சார் சொல்லுங்க சார்.
சத்யா அவங்களுக்கு அன்மியூட் பண்ண சொல்றாங்க. அவங்க தான்
yes,
எம்சி. சத்யாவுக்கு மட்டும்.
டாக்டர் சத்யா ஆனந்தா சார்?
இல்ல சத்யான் ஸ்டூடெண்ட்.
ஓ இப்ப கொடுத்துருக்கேன் சார். அது உங்களுக்கு ரெஜிஸ்ட்ரார்னு ஒன்று வந்திருக்குங்க சார், MTWU.
அப்படியா? அவங்க கிட்ட பேசி பாருங்க. சத்யா நீங்க எம்சி டெஸ்ட் பண்றாங்களா?
சார் நான் எம்சி பண்றேன் சார். சத்யா ஆனந்த் தான் சார்.
உங்களுக்கு வந்துருச்சுல? அப்ப
அது ஒரு நிமிஷம்.
மைக் உங்களுக்கு ஆடியபிளா இருக்கா நாங்க பேசுறது?
எனக்கு ஆடிபிளா இருக்கு சார்.
நீங்க தானே எம்சி டெஸ்ட் பண்றீங்க?
ஆமாங்க சார்.
ஓகேப்பா, அப்போ உங்களுக்கு அன்மியூட் பண்ணியாச்சு. ஓகே. தேங்க்யூப்பா.
தேங்க்யூ சார்.
கண்ணன் சார் அவங்களுக்கு கிளியரா இருக்குது.
ஓகே சார். ஷூர்.
அவங்களுக்கு அன்மியூட் பண்ணியாச்சு.
ஓகே.
அவங்க தான் எம்சி டெஸ்ட் பண்றாங்க.
ஓகே சார்.
விமலா, ஹெச்ஓடி மேடம், புவனேஸ்வரி, ரிஜிஸ்டார், விசி இவங்களுக்கெல்லாம் அன்மியூட் ஏற்கனவே போட்டிருப்பீங்க. கண்ணன் சார்.
சார் சொல்லுங்க சார்.
விசி மேடம், ரிஜிஸ்டார் மேடம், புவனேஸ்வரி மேடம், விமலா, நான். இது ஏற்கனவே அன்மியூட்ல இருக்கு.
ஓகே சார். அவங்க எந்த நேம்ல வந்திருக்காங்கன்னு தெரியுமா சார்?
அந்த இன்விடேஷன்ல பேரு பார்க்கணும். இந்த வர்றேன்.
இல்ல சார், அது ஓகே சார். இதுல உள்ள சப்போஸ் வேற நேம்ல வருவாங்க.
ஓ அப்படி இருக்குமா? அது அவங்க எனக்கு சொல்லலையே. இந்த வர்றேன் பாக்குறேன். விமலா மேடம் இந்த வர கேக்குறேன் சார்.
அவங்களுக்கு கொடுத்துட்டேன் சார். விமலா மேடத்தை கொடுத்துட்டேன், புவனேஸ்வரி மேடத்தை கொடுத்துட்டேன்.
சொல்லுங்க சார்.
மேடம் விசி எந்த பேர்ல உள்ள வருவாங்க? அவங்களுடைய
ப்ரொஃபசர் வைதேகி விஜயகுமார் அவங்க நேம் சார். இன்விடேஷன்ல இருக்கும்.
அந்த பேர்ல வருவாங்களா வேற பேர் எது?
அப்படின்ற நேம்ல வருவாங்க.
விசி பேர்னா
நான் சொல்றேன்.
சரிங்க.
ஆமா ஓகேங்க சார். அவங்க நேம் வைதேகி விஜயகுமார். ஆமாங்க சார்.
மேடம் ஆன் மொபைல் இருக்காங்க டிராவலிங்ல. அதனால மேடம் டவர் கிடைச்சா ஜாயின் பண்ணிரு, இல்லனா வெயிட் பண்ணாம அப்படியே ப்ரோசீட் பண்ணிருங்க அப்படின்ட்டாங்க சார்.
இல்ல அவங்கள நம்ம ஒரு 10:30 10:20 25 வரைக்கும் பார்க்கலாம்.
வந்துறேன்ட்டாங்க. அது ஒண்ணும் பிரச்சனை இல்ல சார். ஸ்டூடண்ட் என்டர் ஆக சொல்லிரலாம் சார். டைம் ஆயிட்டே இருக்கு.
ஆமா சொல்லிருங்க மேடம். எல்லாரையும் சொல்லிருங்க.
விமலா பிரேயர் சாங் சொல்லிருக்கீங்களா?
நான் சொல்லிட்டு இருக்கேன். சொல்லிருக்கேன் மேம். வாட்ஸ்அப் ஃபோன் பண்ணி சொல்லி போட்டிருக்கேன் மேம். போட்டுட்டே இருக்கேன் இப்போ.
சரி டாக்டர்.
ஜாயின் பண்ண சொல்லி.
சத்யா.
சரிங்க மேம்.
மேம் சொல்லுங்க.
சத்யா உள்ள வந்துட்டாங்க மேம்.
மேம் சொல்லுங்க மேம்.
உள்ள வந்துட்டீங்களா? தேங்க் யூ சத்யா.
வந்துட்டேன் மேம்.
மேடம் விசி மேடத்துக்கு நம்ம ஒரு 10-25 வரை வெயிட் பண்ணலாமா?
நான் ஸ்டூடண்ட்ஸ் எல்லாரும் கேமரா மட்டும் அன்மியூட் பண்ணிக்கங்கம்மா. கேமரா அன்மியூட் பண்ணுங்கடா. ஸ்டூடண்ட்ஸ் கேமரா அன்மியூட் பண்ணுங்க.
சார் இப்ப எவ்வளவு பேர் சார் உள்ள இருக்காங்க கான்ஃபரன்ஸ் லிங்க்குள்ளார?
பார்ட்டிசிபெண்டா?
6 பேர்
மேடம்
இருக்காங்க.
66 மேம்.
ஓகே.
66 இருக்காங்க.
லிங்க்ல சார் யூடியூப் லிங்க்ல ஏதோ இருக்காங்களா?
அது வந்திருப்பாங்க.
I will check and inform you ma'am. 1 minute ma'am.
ஓகே.
நான் ஸ்டார்ட் பண்ணிடலாமாப்பா?
விசி வந்து வர சான்ஸ் இருக்கா மேடம்?
சார் மேடத்தை இப்ப கேட்டுறேங்க சார் நானு.
கேளுங்க. ரீஸ்டார்டிங் கேட்டு.
Ma'am 18 members watching in YouTube ma'am.
80 plus 66.
18.
ஓகே.
18. Yes ma'am.
18.
ரெஜிஸ்டர் மேடம்
சரிங்க சார்.
கேட்கலாமா?
ரெஜிஸ்டார் மேடத்துல கேளுங்க ஃபர்ஸ்ட்.
கேட்டுருங்க.
ஏன்னா விசி ஆமா ரெஜிஸ்டார் மேடத்துல.
13 மேடத்துக்கு அனுப்பி இருக்கிறேன் விசி மேடத்துக்கு. இப்ப மேடம் இருக்காங்கன்னா கேட்டு போட்டுறலாம். கேட்டுமா? ஸ்டார்ட் பண்ணலான்ட்டாங்க. விசி மேடம் மட்டும் கேட்டுறேனுங்க சார்.
ரீஸ்டார்ட் வாங்க.
ரெஜிஸ்டர் மேடம் 10:30க்கு ஓகே சொல்லிட்டாங்க. ப்ரோக்ராம் விசி மேடத்தை மட்டும் இப்ப கேட்டுறேனுங்க சார்.
கேட்டால் 10:30க்கு ஆரம்பிச்சிடலாம்.
ஆமாங்க சார். Ma'am, good morning, ma'am.
Good morning.
Good morning, madam.
Good morning, sir.
Ma'am.
VC madam join பண்றாங்களா?
ஆமாங்க மேம் பண்றாங்க மேம் இப்ப பண்றேன்னு இருக்காங்க மேம்.
ஓகே ஓகே அப்ப வெயிட் பண்ணலாம்.
ஆமாங்க மேம் ஒரு 5 minutes மேம்.
ஓகே ஓகே
Hello.
Yes, madam. Good morning.
Hello. Shall we start?
Yes, madam. Good morning, madam.
Ma'am, good morning, ma'am.
Good morning.
Good morning, madam.
Good morning, ma.
Good morning, madam.
Good morning.
Shall we start, ma'am?
Kannan sir, ready இருந்துக்கோங்க.
Madam வந்துட்டாங்க.
Yes, sir. Yes, sir.
ரெக்கார்ட் பண்ணுங்க மேடம். சார் ரெக்கார்ட் பண்ணிக்கோங்க.
Shall we start?
Yes, madam.
Good morning and greetings to everybody. It is a spectacular day in the history of Mathematics Department of Teresa Women's University that organizes an international webinar on the celebration of the 133rd birth anniversary of Ramanujam, who had contributed enormously to mathematics. In fact, Mathematics Department of Teresa Women's University has Ramanujan Mathematics Club since 2012, which is an integral part of the department. The invocation to Mother Tamil describes Her Majesty beauty, purity, and fame, and praises her. I humbly request through Thank you. It is my pleasure to invite Dr. K. Bhuvaneshwari, Head of the Department of Mathematics, Teresa Women's University, to give a warm welcome to our esteemed guests of honor and the learned gathering.
Bhuvaneshwari, your voice is not audible.
Yes, ma'am.
கண்ணன் சார் புவனேஸ்வரத்துக்கு ஆடியோ கொடுங்க சார். கண்ணன் சார்.
சார் அவங்க எனேபிள் பண்ணிட்டாங்க சார்.
Good morning.
Good morning.
Good morning, ma'am. Sorry, ma'am. Good morning to all. Sir, என்னோட voice audible இருக்காங்க sir? Okay. Good morning to all. First of all, I thank Almighty to make us to be this wonderful occasion. On behalf of Ramanujam Mathematical Club, Mother Teresa Women's University, I welcome you all in 3 days international webinar on applied mathematics. First of all, I welcome our Honorable Vice Chancellor, Dr. Vaidegi Vijayakumar, who is the women fit to this word. Successors are not doing different things. They are doing things differently. As our madam is fit to that. She is a dynamic, dedicated, hard work, faith, God believing women. Ma'am, we are very happy to invite you, very happy to welcome you in this 3 days international webinar. Welcome you, ma'am.
Thank you, madam. Thanks.
Next, I welcome our beloved Registrar, Dr. C. Hilda Devi, Mother Teresa Women's University, Kodaikanal. Madam is fit to the word, speak less, work more. I learned many things from Madam. Madam, you are the backbone for all our administrative activities. Welcome you, ma'am.
Thank you. Thank you.
Next, I welcome our invited speaker, Dr. Rajesh, Assistant Professor, Department of Mathematics, Ramanujan College, University of Delhi, who is going to give the topic graphs with equal domination and independent domination numbers. And another session, Dr. S. Resort, Professor, Department of Mathematics, University of Kashmir, in the title on Laplacian eigenvalue of the graph. I welcome both the resource persons, both the speaker in this webinar. Next, I welcome, I extend my hearty welcome to Professor A.N. Mohammed, Department of Mathematics, College of Natural and Computational Science, Bulhara University, Bulhara, Ethiopia. Sir is going to give a topic title, Graph Theory Act as a Major Role in Mathematics and Engineering Application. Welcome, sir. And on behalf of Ramanujan Mathematical Club, I invite Tamarai Thangam ma'am, Department of Nursing, since our webinar topic is an applied mathematics. So a person from the outside of mathematics department, College of Health and Medical Science, Bulhara University, Ethiopia. Madam going to give there is a topic in magnitude and determinant factor of Manchurian using biological modeling. Next, I welcome Dr. Ramagopalan Nalan, Associate Professor, Department of Mathematics, College of Natural and Computational Science, Bulhara University, Bulhara, Ethiopia. Sir going to deliver a address in significance of numerical methods in computation fluid dynamics on behalf of our mathematics club. Welcome you, sir. Another resource person from women, Professor Dr. C. Sivanyanam, Assistant Professor, Department of Mathematics, University of Technology and Applied Science, Oman. Sir going to deliver an address in the title, Impact of Various Domination Parameters in Graph. Welcome you, sir. And two more person from our Tamil Nadu, title, A New Class of Bimagic Tree. The person, Dr. A. Soleraj, Associate Professor, Department of Mathematics, Jamal Muhammad College. Sir is also our organizing secretary, one part of an organizing secretary. On behalf of Mother Teresa Women's University, I welcome you, sir. Next, I welcome Dr. G. Mahadevan, Assistant Professor, Department of Mathematics, Gandhigram Rural Institute, Deemed University, Gandhigram, Dindigul. Sir going to give a lecture in application of graph in science and technology in 24 on behalf of our mathematics department. Welcome you, sir. Apart from, I welcome all the professors who are in the audience and the online webinar and research scholars and my dear beloved students. Welcome you all for this 3 days webinar. Thank you.
Thank you, ma'am. It was an apt welcome address to our respected guests. It is my honor to invite Dr. Vimala, Assistant Professor, Department of Mathematics, Teresa Women's University, introduce our Registrar in Charge, Dr. Hilda Devi, Madam, to the gathering.
Very good morning, madam. Good morning, ma'am.
Good morning. Good morning.
A very pleasure. Good morning to one and all gather here. It's a great pleasure for me to introduce Registrar Ma'am, who received distinct awards achievements. Yes, I'm speaking about Dr. C. Hilda Devi, Registrar Madam, Mother Teresa Women's University, Kodaikanal. She has 31 years in teaching experience and 34 years research experience. She crossed many positions as DEU in charge, NSS, RRC, Director in charge of Women's Studies, Coordinator of a Center for Gandhian Studies, Controller of Examination in charge, and a Steering Committee member. She is a professor and head of the Department of Sociology, Mother Teresa Women's University, Kodaikanal. Her area of research in sociology, social work, and women studies. She produced 6 PhDs, 31 MPhils, and a number of PG, UG levels students. Madam published nearly 50 publications in national, international seminars and conferences. Madam successfully completed 7 funded projects from UGC, ICSSR, IWID, CWS. For her dedication, she received a certificate of commemoration from Mother Teresa Women's University, Best Women Professor Award in Social Science, Best Senior Social Scientist Award. Madam organized 21 conferences in national and international level, 9 international level interaction sections, 8 women's empowerment training programs. Madam organized 4-week entrepreneurship development program funded by DST and 3 faculty development programs. Madam proved her research through paper presentation in state level, international level, and national level seminars, conferences. Madam, as a member of professional bodies, as the advisory board member of ICSSR project, and she did many academic roles. The council member in Mother Teresa Women's University. Enthusiasm is important in teaching because it helps to motivate students to learn and will encourage them to maintain a positive towards their work. I'm glad to see you, madam. Welcome you, madam. Thank you, ma'am.
Thank you.
Thank you, ma'am. Inaugural address is a moment when an academic institution can affirm its past, define its purpose, and interprets its role to a wide audience. I warmly invite Dr. S. Hilda Devi, our registrar in charge, to deliver inaugural address. I welcome you, ma'am.
Respected Vice Chancellor, Madam, Dr. Vaidehi Vijay Kumar, Mother Teresa Women's University, and our beloved convener and organizer, Dr. K. Bhuvaneshwari, Associate Professor and Head in charge of Department of Mathematics, Mother Teresa Women's University, Organizing Secretaries, Dr. S. Vimala, Dr. A. Sole Raju, team members, Dr. S. Jayashree. On behalf of Mother Teresa Women's University, I am very glad to extend a warm and pleasant good morning to one and all on these 3 days international webinar on applied mathematics scheduled on 22nd to 24th December 2020. I am happy to see you all in this international webinar. And when I gathered information about applied mathematics, I came to know that it involves the application of mathematics to the problems which arises in various areas like science, engineering, social sciences, and other diverse areas. And it is the development of new or improved methods to meet the challenges of new problems. Accordingly, when I have seen the program schedule, the topics have covered almost all the areas. So when the question comes whether applied mathematics is useful, the answer is definitely useful. And also, contrary to the popular belief of the school students used to feel scared of mathematics on board of the mathematical works and meticulous work, it proved as a useful subject. But we must also remember that without mathematics, we cannot imagine the financial aspects starting from individual, home, and also at a global level. So it is an essential and inevitable one. One must know the importance of the mathematics, especially applied mathematics. The mathematical skills will be of quite useful for a variety of careers, and it plays an important role in practical sciences too. Even though students find that mathematics is one of the complicated subjects, some others find that it is an interesting subject. There are many openings for mathematicians. Wide variety of career opportunities are also open to people with mathematical training and talent. Especially in applied mathematics, when we look for important connections with other disciplines that may give interesting and useful mathematics, whereby innovative mathematical reasoning, which may lead to new insights and applications. And we are waiting to listen to the experiences shared by the eminent people who are going to deliver the address today. So accordingly, in these 3 days international webinar on applied mathematics, the invited resource person and speakers are going to share their views. I'm glad to welcome all the 10 speakers who are ready to deliver their rich experiences on today's topics effectively. Also, thank you all to all the participants present here to pay your attention and learning from the topics you are going to listen today. So I am very happy to know about this relevance of this topic, and the organizers are have taken painful efforts in organizing this 3 days international seminar. So once again, I would like to congratulate the organizer and the organizing secretaries. And on behalf of Mother Teresa Women's University, I wish this 3 days webinar with, to conclude with grand success. Thank you very much.
That was really an amazing inaugural speech. Thank you, ma'am. It is my great honor and indeed a rare opportunity and privilege to introduce our honorable and esteemed leader, Dr. Vaidehi Vijayakumar, the Vice Chancellor of our alma mater, who inspires us to do things that we have never thought we could. Our esteemed leader, Dr. Vaidehi Vijayakumar, is aware that the university is not merely an examining body. It is primarily a nursery of good citizens. Therefore, she emphasizes the diffusion of scientific, technical, and professional knowledge on the one hand, and building up of character in young women and personality development, an integral part of education on the other through the vision and mission of our institution. Our respected Vice Chancellor has a very high and marvelous profile, and it is a Herculean task of comprehend her academic achievements. Yet humbly, I will try to highlight some of her accomplishments. The career objective of Dr. Vaidehi Vijayakumar, Vice Chancellor, itself speaks volume.
Please skip this because all of our students know about this. Directly, we can go for presidential address. Okay.
Okay. Thank you. Our leader, Dr. Vaidehi Vijayakumar, our Vice Chancellor, inspires us to do things that we have never thought we could. I invite our Honorable Vice Chancellor of our alma mater to deliver the presidential address. I welcome you.
Very warm good morning to one and all present here. Respected, am I audible?
Yes, ma'am.
Yes, audible.
Respected Registrar, Dr. Hilda Devi. Respected Head of the Department, Dr. Bhuvaneshwari. Respected Mathematics Department Faculty, Dr. Vimala. Respected speakers, 10 members who will be contributing towards this 3 days international webinar. And I'm very happy to know that because of Ramanujam's birthday, 3 days international webinar is arranged by Mathematics Department. The topic is Applied Mathematics. The mathematics is basically the foundation of computer science and any other mechanical or electrical or any commerce courses, arts and science engineering courses. It is the pioneer, that is Ramanujam, has given lots of insight into the mathematics and made things very, very simple. India is one of the important country which has used mathematics in calculating when the lunar eclipse or solar eclipse is supposed to come, and they have divided the whole universe using stars, either lunar or solar, and they are very strong in mathematics. And obviously Ramanujam is one of the important person who has done lots to mathematics. Mathematics, when we talk about computer science, the graph theory is trying to give you the methodology by which your operating system can be linked and what will be the vertices, what will be the edges, and apart from this, how to definitely optimize the whole resources that are being used, including cache memory, CPU, etc. So when we talk about optimization, obviously this optimization is being used in electrical also. Without mathematics, none of the PhD is basically valid. When people perform experimentation, definitely they have to have a qualitative model and they have to substitute some quantity in order to ensure that qualitative models are working. So modeling has become very important. And when we talk about electricity, we have to definitely optimize electricity by calculating the load, how to distribute the load, etc. When we talk about electronics, the mobility of electrons and when exactly the current is supposed to flow, when the current is not supposed to flow in a device, all these things are mathematically modeled. And now if we see the very important trend of artificial intelligence, machine learning and data science, without mathematics, nothing is possible. So obviously the data science is giving a predictive model, and using these predictive models, it is possible for any business people to understand the business models and suggest a solution for getting a best profit. So obviously mathematics is a foundation and it has got its own important role in all the fields of art, science, medicine and engineering. So I congratulate Dr. Bhuvaneshwari for organizing this. I wish all the best for all the participants. And if you are very strong in mathematics, obviously you can become a scientist, especially data scientist. And important is basically the probability theory. And don't be afraid of mathematics. Love it, use it, and whatever you do, have a model and prove that your model is successful in predicting things. So I wish all the best for all the participants. And if you have any grievances, please send a mail to pcmotherteresa@gmail.com. We are ready to support you. Ours is the only women university in Tamil Nadu state. And thanks for joining our university. And if you have difficulty in understanding mathematics, definitely it is possible for us to give you extra support because we have a slow learners coaching method and making things achievable by practice. And we have lots of computer-oriented learning. We support MOOC courses. So obviously, our intention is the students should learn and they should compete and they should be in a position to become a successful career-oriented women, because our objective is Sari Nigar Samanam, that means towards equal status. That is possible only if you have very strong foundation in mathematics. So please do well and please give the feedback and wish you all the best. Thank you very much for the opportunity.
Thank you, ma'am. Thank you, ma'am, for your profound, knowledgeable, encouraging, motivational, and authentic presidential speech. Thank you so much, ma'am.
Thank you, ma'am.
Thank you.
Satya.
Yes, ma'am.
Satya, continue பண்ணுங்க Satya.
Sharmila will continue, ma'am. First time.
Satya, சந்தியாவை present பண்ண சொல்லுங்க.
Sharmila, Maithili. Sharmila.
சத்யா, சந்தியாவை அப்படியே present பண்ண சொல்லிருங்கம்மா.
எப்படி சொல்லிட்டேன் மேம். Sandhya?
Ma'am. Start பண்ணிடுவா ma'am.
Start பண்ணுங்கப்பா, start பண்ணுங்க.
Okay. I'm Sandhya from Mathematics Department, Mother Teresa Women's University. Mathematics is the language with which God has written the universe. Now I am enthusiastic because all great mathematicians are gathered here. A great and good morning to one and all present here. India celebrates 22nd December every year as the National Mathematician Day to honor the birthday of the great mathematician Srinivasa Ramanujan. The world will always grateful to him for his contribution in mathematics. In this wonderful moment, I wish to share few things about the great mathematician Srinivasa Ramanujan. When Ramanujan was 13, he could work out Loni's theorem trigonometry exercise without any help. He was the first Indian who to be elected the Fellow of Trinity College, Cambridge. His formulas, theories, and equations opened an entire new area of works and inspired further research. Nearly all his claims have now been proven right. Srinivasa Ramanujan was only second Indian to be offered fellowship in Royal Society. There is a dedicated museum shooted in Chennai in the glorious memory of Srinivasa Ramanujan. Ramanujan lived just for 32 years, but during this short span, he produced the theorem formulas which even today remains unfathomable in the present age of supercomputers. He's left behind him about 4,000 formulas and theorems. A biography of Ramanujan titled The Man Who Knew the Infinity of published in 1991. The legendary mathematician Srinivasa Ramanujan made extraordinary contribution to the mathematical analysis, number theory, infinite series, and continued fractions. He was the self-taught mathematician who made extraordinary contribution to the world of mathematics. The former Prime Minister of India declared this day as the National Mathematician Day on February 26, 2012. When he was to visit the Madras University in order to pay tribute to the Ramanujan achievements. This main objective behind the celebration is to raise the awareness among the people about the importance of mathematics for the development of humanity. An equation means nothing meets unless they express the thoughts of God. Happy National Mathematics Day to all. Thank you for giving the wonderful opportunity. Thank you.
Thank you, Sandhya. Satya.
Thank you, Sandhya, for your brief and informative introduction about Dr. Ramanujam. Sharmila will continue.
Sir, Sharmila unmute பண்ண சொல்றாங்க சார்.
ஷர்மிளா அன்மியூட் பண்ணுங்க சார். கண்ணன் சார். கண்ணன் சார்.
சார் பண்ணியாச்சுங்க சார்.
கொஞ்சம் வாட் ஆஃப் தேங்க்ஸ் முடிச்சாங்கன்னா அடுத்த செக்ஷன் போயிடும். ஓகே.
ஷர்மிளா, வாட் ஆஃப் தேங்க்ஸ் முடியுமா? இவங்கள அன்மியூட் பண்ண சொல்லுங்க சார்.
பண்ணிட்டாரு.
Yes.
Give us a hearty welcome, big and warm enough to encompass you all. Welcome everyone. This is our very first session on 3 days of international webinar on applied mathematics organized by our Department of Mathematics, Mother Teresa Women's University, Kodaikanal. It's my pleasure to welcome Dr. Rajesh sir, Assistant Professor, University of Delhi. Welcome sir. I kindly request Ms. Hinduja to give and discuss about our honorable speaker, Dr. Rajesh sir.
Good morning to all dignitaries, guests, and delegates with a great joy and immense exaltation. I feel privileged to extend my warm welcome to all present here for the celebration of this occasion. I am profusely elected to take an opportunity to introduce and honor welcome Dr. Rajesh Singh, Assistant Professor, the Department of Mathematics in the University of Delhi. Welcome you, sir. For this dedication, he received a lot of distinctive achievements like South Campus Endowment Scholarship for being the meritorious student in MSc Mathematics. That is, he pursued MSc Mathematics first rank in South Campus, University of Delhi, and first rank in Sri Venkateshwara College, University of Delhi, so on to tell. Sir published 6 international journal paper and 3 were accepted. He dedications towards his responsibility. He is a member in administrative responsibility such as member of placement cell committee, member of web committee, and member of magazine committee in Ramanujan College. In addition, he attended 17 conferences and workshops held over in India. Not only in India, he attended 2 abroad conferences and workshops such as Sir attended a SIMPA Research School Graph Theory organized by Lebanon's University, Beirut, Lebanon as a speaker on the topic graphodial covering member and graphodial length of graph. And this session is fulfilled by the speech on the topic about graph with equal domination and independent domination number. On behalf of the management, I thank him for providing his gracious presence to join us today to enhance our joy. Once again, I welcome you, sir.
Thank you, Ms. Hinduja, for your address. I consider it a great honor to welcome Dr. Rajesh sir onto the session.
கண்ணன் சார் ராஜேஷ் சார் வர்றாங்க. கண்ணன் சார் கண்ணன்
சார்
ராஜேஷ் சார் லிங்க்ல வர்றாங்க, கொஞ்சம் அவர் அலோவ் பண்ணுங்க.
ஷியர் சார். எஸ் சார். எஸ் சார்.
ராஜேஷ் டெல்லி ராமானுஜம்
எஸ் சார்.
சார் இப்போ வருவாங்க.
ஓகே ஷியர் சார்.
அவரை பத்தி திரும்ப இன்ட்ரோடியூஸ் பண்ணாலும் பண்ணி சொல்லுங்க திரும்ப.
எஸ் சார்.
அவர் கேட்கல. ஏன்னா அவர் இப்பதான் உள்ள வர்றாரு, அவரை பத்தி கொஞ்சம் பிரீஃபா சொல்லுங்க.
ஷியர் சார். ஷியர் சார்.
ஃபர்ஸ்ட் அவர் வந்துட்டாரான்னு சொல்லுங்க.
ஓகே சார்.
சார் ஜாயின் பண்ணிட்டாருங்களாங்க சார்?
ஆமா ஜாயின் பண்ணிட்டாரு, இந்த வந்துட்டாரு கோஸ்டார் நவ் வந்துட்டாரு. மேடம் திரும்ப கொஞ்சம் அவரை இன்ட்ரோடியூஸ் பண்ண சொல்லுங்க.
ஷர்மிளா ப்ளீஸ் இன்ட்ரோடியூஸ் மா. ஷர்மிளா
Sir, thank you. Good morning, sir. Good morning, sir.
Good morning, Professor Solaraj.
Welcome to Mother Teresa Women's University Department of Mathematics.
Thank you, ma'am. Thank you.
Sir, please wait. We are introducing you, sir.
Okay, okay.
I kindly request Ms. Hinduja to give and discuss about a honorable speaker, Dr. Rajesh sir.
Good morning to all dignitary guests and delegates with great joy, immense and exaltation. I feel privileged to extend my warm welcome to all present here for the celebration of this occasion. I am profusely elected to take an opportunity to introduce our honor to welcome Dr. Rajesh Singh, Assistant Professor, Department of Mathematics, University of Delhi. We welcome you, sir. For his dedication, he received a lot of distinct achievements like South Campus Endowment Scholarship for being the meritorious student in MSc Mathematics. That is, he pursued MSc Mathematics first rank in South Campus University of Delhi and first rank in S.T. Venkatesha College, University of Delhi, and so on to tell. Sir published 6 international journal papers and 3 were accepted. His dedication towards his responsibility, he is a member in administrative responsibility such as member of placement cell committee, member of website committee, member of magazine committee in Ramanujan College. In addition, he attended 17 conferences and workshops held over in India. Not only in India, he attended 2 abroad conferences and workshops such as Sir attended Simpa Research School Graph Theory, organized at Lebanon's University, Beirut, Lebanon on speaker on the topic graphoidal covering member and graphoidal length of graph. And this session is fulfilled by his speech on the topic about graph with equal domination and independent domination number. On behalf of this management, I thank him for providing this gracious present to join us today to enhance our joy. Once again, I welcome you, sir.
Thank you, Hinduja, for such a nice introduction. So first of all, I would like to thank the organizers of this conference for giving me this opportunity to be a part of this wonderful conference and to present here. So, and I would also like to thank Professor A. Solai Raju for his invitation. So let me start my topic.
Yes.
So
yes, sir. Yes, sir.
So is my screen visible?
Audible, visible.
Okay. So my talk is titled with graphs with equal domination and independent domination number. So I'm Dr. Rajesh Singh from Ramanujan College, University of Delhi. So this talk is based on the 2 graph theoretic parameters, domination number of a graph and independent domination number of a graph. So both the parameters are based on the notion of domination in graphs. So what is domination in graphs? So given any graph G, a subset D of the vertex set V is called a dominating set of G if for every vertex V in V minus D, there exists a vertex U in D such that U is adjacent to V. That is, every vertex outside D is adjacent to some vertex in D. So such set will be called a dominating set. Then the domination number, which is denoted by gamma G, is the minimum cardinality of a dominating set in G. So gamma G is minimum of cardinality of D, where D is a dominating set of G. A dominating set of G with cardinality gamma G is called a gamma G set of G. So let us look at this example. So in this example, I have a graph with order 8. So as you can see, I have partitioned the vertex set into 2 sets, D and V minus D. So the set D, which is consisting of the vertex 0 and 1, is a dominating set of this graph G. And as you can see, every vertex which is not in D is dominated by either 0 or 1. So this graph D is a dominating set of G. And it is easy to see that if I reduce the number of vertex, that is, if I take any set with cardinality 1, then it cannot be a dominating set of G. So for this graph, its domination number is 2. So these are the 2 fundamental books on domination. So first is Fundamentals of Domination in Graphs, and second consists of advanced topics for domination in graphs. So anyone who is interested in pursuing research in domination must have these 2 books for reference. And these 2 books are edited by Haynes, Heditnemi, and Slater. So the origin of domination lies in an attempt to solve the famous chessboard problem. So what is a chessboard problem? It is to find the minimum number of coins that can be placed on an n cross n chessboard such that every square on the chessboard is either occupied by one of the coins or it can be attacked by one of these coins. So basically, what is the problem? If we are given any chessboard, so generally we have seen an 8 cross 8 chessboard. So if we're given an 8 cross 8 chessboard, so we have to find how a minimum number of coins that we can put on the chessboard so that every square which are not having the queen must be attacked by one of these coins. So this is the chessboard problem. So how a queen attack on a chessboard? So a queen attack on a chessboard horizontally, vertically, and diagonally. That is, if we have any square that is in the same row of the queen, then it will attack that square. And similarly, it will attack any square that is on the same column, and it will also attack any square that is on the same diagonal of the queen. So let us represent this chessboard problem and the attack of this queen on a chessboard by a graph. So how to represent this? So for this, what we do, we take the squares of the chessboard. So what we do, we take the squares on the chessboard of the as the vertices of the graph, and since our queen can move horizontally, vertically, or diagonally, so we make any two vertices of this graph adjacent if they lie on the same row, same column, or same diagonal of the chessboard. And the graph that's obtained, which represents this chessboard, it is called the Queen's graph. So the Queen's graph Qn of order n square had squares of an n cross n chessboard as its vertices, and we make two squares adjacent if they are in the same row, same column, or same diagonal. So with this representation, the problem of finding minimum number of queens on the chessboard such that every square is either occupied by a queen or is attacked by one of the queens is equivalent to finding a dominating set of minimum size in the graph corresponding to the chessboard. So that is, the chessboard problem is equivalent to finding the domination number gamma qn of the Queen's graph. So let us first let me explain you this how we have represented this graph. So for this, is my screen visible?
Yes sir, yes sir.
Okay, so this board is visible to everyone? Is this board visible? Whiteboard?
Yes, visible sir.
Okay, okay, so fine. So let us take a 2x2 chessboard. Okay, so I am taking a 2x2 chessboard. So this is my this is my first square, this is second square, this is third square, this is fourth square. So how we represent this by a graph? So what we do, we take the vertices one. So we take the vertices of the graph, the squares of the graph as the vertices of the graphs. So I've taken these as vertices of the graph, and what we do, we make two squares adjacent if they are in the same row, same column, or same diagonal. So in this case, as you can see, 2 is in the same row as 1, so I am making 1 and 2 adjacent. Similarly, 4 is in the same diagonal of 1, so I am making 4 and 1 adjacent. Then 3 is adjacent to 1 because 3 and 1 are in the same row. Similarly, if we can draw the complete adjacencies, then we will get this graph. So this is our Q2, and this is isomorphic to complete graph K4. So what is the domination number of this graph? If we take any vertex, then and so any vertex outside this vertex is dominated by this. So domination number of Queen's graph Q2 is 1. And similarly, if you place any queen on this square, so it will dominate this, it will also dominate this, it will also dominate this. So all the squares are either attacked by the queen or is occupied by the queen. So minimum number of queens required as per the chessboard problem is 2. Okay, fine. So now let us move back to our presentation. So this is another example. Here I have a 3x3 chessboard and I have represented its graph Q3. So as you can see in the diagram, because 2 and 3 are in the same row as 1, so I made 1, 2, and 3. adjacent to each other. Similarly, 1, 4, and 7 are adjacent. 1, 4, and 7 are adjacent. 1, 4, 7, 1, 2, 3. So, and 1, 5, 9 is also adjacent. This 1 is, here is 1, 5, and 9. So all these are all adjacent. So this is how we obtain this Queen's graph Q3. And as you can see, if I take 1 and 6 in this case, then it will dominate all the remaining vertices of this graph. So its domination number is 2. So, and if I put my queens on these two squares, 1 and 6, then they will dominate all these. So this will be dominated by this. It will dominate these two and this, and remaining this will be dominated by 6. So all the squares are dominated by either 1 or 6. So minimum number of queens required to cover 3 cross 3 chessboard is 2. So here is another answer to an 8 cross 8 chessboard. So if I will place my queens at these places, so this place, and this place. So if I place my queens at these places, then they will attack all the squares of this chessboard. So domination number of Q5 in this case is 5. And this is not a unique solution. There are other solutions. So there are other places where you can put your 5 queens and you can attack all the squares of this chessboard.
5.
Okay. So now in this table, I have represented the domination number of queens graph for n equal to 1 to 19. So for n equal to 1, 2, and 3, its domination number of the queens graph is 1. For n equal to 4, it is 2. For n equal to 5, 6, it is 3. For n equal to 7, it is 4. For n equal to 8, domination number of queens graph is 5. For n equal to 9, it is again 5. For 10 and 11 also, it is 5. Then for 12, it is 6. For 13, it is 7. And for 14, it is 8. For 15, 16, and 17, it is 9. And for 19, it is 10. And domination number beyond this is not known yet. And to solve these problems, you need to develop algorithm and computer program, because these numbers are very large. See, the order of this Queen's graph for n equal to 10 is 100. So you need to have a computer program and an algorithm to get these domination numbers of these Queen graphs. Okay. So now let us move to the main theme of our talk. So which is the graph satisfying the equality of the domination number and independent domination number. So what is independent domination number? So a subset D of a vertex set Vg will be called an independent dominating set if it is independent and it is dominating as well. So any set which is independent and dominating will be called an independent dominating set, and the minimum cardinality of an independent dominating set of the graph G is called independent domination number, and it is denoted by Ig. And any set with any independent dominating set with cardinality Ig will be called an Ig set of G. So now, since every dominating set of a graph is an independent dominating set, because by definition it is dominating, so every independent dominating set is a dominating set as well. So the set of all dominating sets of G is a subset of the set of all dominating sets. Hence, the minimum of the cardinality of D, where D is a dominating set, will be less than equal to the minimum of the cardinalities of D, where D is an independent dominating set of G. And hence, we have the inequality domination number less than equal to its independent domination number. So let us take this example. So in this example, I have two graphs. So in the first graph, I have taken a graph in which domination number is equal to its independent domination number. So as you can see, this set dominates all the remaining vertices, but this is not independent. But if I take these two vertices, this vertex and this vertex, then these two dominates all the remaining vertices and they are independent as well. So for this graph, domination number is equal to its independent domination number, and which is equal to 2. And on the right side, I have another graph G2 in which domination number is not equal to independent domination number. So the vertices marked in red, these three vertices, they are a dominating set, but since they are not independent, so, and if I take any set with cardinality 3, then it will not form an independent dominating set. So the the set with minimum cardinality 4 and which is independent dominating set is 0, 5, 6 and 7. So if I take So if I take 0, 5, 6 and 7, then they will dominate all the remaining vertices of this graph. So this set 0, 5, 6, 7 is an independent dominating set of this graph. So here is a comparison between domination number and independent domination number of Queen's graph. So in this table, as you can see, the domination number is equal to independent domination number for n equal to 1 to 18, except in the case when n is equal to 4, n is equal to 6, n is equal to 12, and n is equal to 18. So except these, at all other places, the domination number happens to be equal to the independent domination number of the Queen's graph. For n equal to 19, independent domination number of the Queen's graph is not known yet. It is either 10 or 11, but we don't know which one of these is the independent domination number of this Queen's graph. And beyond that, we are still to find independent domination number, but we have certain results for independent domination number and domination number of a Queen's graph. So these are some results based on domination number and independent domination number. So in the first result, we have a lower bound, which is n minus 1 by 2. So domination number is always greater than equal to n minus 1 by 2 for any n belonging to the set of naturals. And since independent domination number is always greater than equal to the domination number, so this inequality is true. Now for n equal to 3 and 11, it has been proved that domination number of the Queen's graph is equal to its independent domination number, and which happens to be equal to n minus 1 by 2. And if we take n to be any natural number which is not equal to 3 and 11, then domination number is always greater than equal to the CL of n by 2. And because the independent domination number is always greater than this, so this inequality is there. Then next we have a conjecture. So in this conjecture, it has been, so in this conjecture, it is said that independent domination number is less than equal to CL of n by 2 plus 1 for every natural number n. And for n equal to 1 to 20, it has been proved to be true. But for other values, it is still to be explored. And one more result that I have forgot to mention is that this result is very important. It is an elementary result. So domination number of Qn plus 1 is less than equal to domination number of Qn plus 1. And why it is elementary? Because if I take any, this is suppose my any n cross n chessboard. So this is an n cross n chessboard. So for n plus 1 chessboard, what I will do? I will have to just add these one row and one column. So any dominating set of this along with this will dominate this complete graph n plus 1 cross n plus 1. So Qn plus 1 will be dominated by any dominating set D along with this vertex. So gamma of Qn plus 1 will always be less than equal to gamma of Qn plus 1. So this result is very useful in exploring domination number of Queen's graph and its independent domination number. So the two parameters, domination number and independent domination number, can be equal for infinitely many graphs. And the following theorem proves this fact. So if I take any graph and if I take its corona graph, then the domination number of the corona graph will be equal to its independent domination number, which will be equal to the cardinality of the graph. So for example, if I take the C4, so this is our C4, and if I take C4 corona K1, so what will be this graph? So C4 corona K1 is nothing but this graph, right? And we know that every minimum dominating set contains all the support vertices. So these four vertex must be in some minimum dominating set. So gamma of C4 corona K1 is equal to 4. And if I, because each vertex in this case is a support to exactly one pendant vertex, so if I take the set of all pendants, then it will form a independent dominating set. So independent domination number of C4 corona K1 is also 4. So in this case, domination number of corona of C1 is equal to independent domination number of corona of C1. Okay. Again, the difference is, in the last example, we have seen that the two parameters can be equal for infinitely many graphs. Now, in this example, we will see that the difference between these two parameters, we can make it arbitrarily large. That is, if we take any positive integer k, then we will be able to find a graph for which the difference between the independent domination number and domination number will be equal to k. And one such graph is this double star. So difference between independent domination number and domination number of double graph is equal to minimum of st minus 1. So if we take any double star DST, so what we will take? We will take dk plus 1 and k plus 2. So for this, for any k belonging to z positive, if I take any k belonging to z positive, and if I take this double star is this graph. So at one place I am taking k plus 1 pendants, at other place I am taking k plus 2 pendants. Then independent domination number of this graph, if I take it equal to g, so independent domination number of g minus domination number of g will be equal to minimum of this k plus 1 and k plus 2, which will be equal to minimum of k plus 1, k plus 2 minus 1, which is k plus 1 minus 1, so k. So independent domination number minus domination number happens to be equal to k in this case. So for any positive integer k, we can always get a graph with difference between domination number and independent domination number equal to k. Okay, so thus we have seen that in general the two parameters are not always equal, and characterizing graphs satisfying the equality of domination and independent domination number is a long-standing problem, and it has attracted a lot of researchers over the years. So these are some of the significant papers on the equality of domination and independent domination number. So in the first paper by Allen and Elsker, they have proved that every claw-free graph satisfies the equality domination number and independent domination number. Then in this third paper, complete characterization of trees satisfying the equality is given, and other paper also contain results based on domination number equal to independent domination number. So trees, for any given tree, the characterization of trees satisfying the equality gamma t equal to it was first given by Harare and Livingstone but their characterization was complicated and difficult to apply. So with the motive to attain a simpler characterization, Cocaine and others, they gave another characterization for trees satisfying the equality gamma t equal to IT, and for that they analyzed the vertices present in all the minimum dominating sets of the trees. So this is the theorem. So in this, what they have done, they have taken two sets, AT, which is consisting of vertices which are present in every dominating set, and they have recursively defined another set, IT, and then they have proved that for any tree T, the domination number equals independent domination number if and only if the set AT union IT is independent. So trees satisfying gamma t equal to IT are completely characterized, but the general problem of characterizing graphs with satisfying the equality gamma equal to IG is still an open problem. So it is an open problem to characterize graphs with equality gamma equal to IG. So in the year 1978, Alan Lasker proved that being claw-free is sufficient for a graph to satisfy gamma equal to IG. So they have shown that if we have any graph which does not contain any induced subgraph isomorphic to the claw K13, then the domination number of that graph will be equal to its independent domination number. And we denote the family of claw-free graphs by F1. So F1 denotes the family of claw-free graphs. Then in 1991, Top and Walkman extended the Alan-Lasker theorem, and they provided 16 graphs such that if a graph has no induced subgraph isomorphic to one of those 16 graphs, then that graph must satisfy the equality of domination number and independent domination number. So these are the 16 graphs, H1, H2, H3, H4, and up to H16. And if a graph does not have these as an induced subgraph, then that graph must satisfy the equality gamma equal to IG. But obtaining a complete characterization of forbidden subgraph for the equality of domination number equal to independent domination number is impossible, because if I have any graph and if I make all the vertices of that graph equal to adjacent to any other vertex, so let me show. So if I have any graph G and if I take another, so if I take an H to be the graph in which all the vertices of G are adjacent to this vertex, then domination number of H will be equal to independent domination number of H will be equal to 1. So this vertex will dominate all the vertices of this graph. So domination number of H will be equal to IH equal to 1. And as you can see, G is an induced subgraph of H. Hence, we have a graph. So for any graph, we can have a graph satisfying the equality which can contain any graph as its induced subgraph. Hence, we can never. So it is impossible to obtain a forbidden subgraph characterization for equality of gamma equal to I. So it is impossible to obtain a forbidden subgraph characterization. So if I let F1 to be the family of claw-free graphs, which was given by Alan Lasker, and if we take F2 to be the family of HI-free graphs, which was given by Top and Walkman, then the family F1 is always contained in F2. That is, the graph satisfying the Top Walkman sufficient condition will always be a claw-free graph. Sorry, a claw-free graph will always satisfy the sufficient condition of Top and Walkman. So Alan Lasker theorem can be obtained from Top Walkman theorem. So what is our contribution on this equality? So this further contents in this presentation is based on the following research paper, which talks about graphs with equal domination and independent domination numbers. And this was published recently in AKC International Journal of Graphs and Combinatorics. So next we present a theorem given by us. So in that paper we have presented a theorem which gives a sufficient condition for a graph to satisfy the equality of the parameters domination number and independent domination number. And in that we have also proved that the theorem by Allen-Lasker and Tock-Bachmann theorem happens to be a corollaries of our theorem. That is, we can derive Allen-Lasker theorem and Tock-Bachmann theorem directly from our theorem. And we also exhibit several classes of graphs where our sufficient condition is satisfied, but Allen-Lasker theorem and Tock-Bachmann theorem are indecisive in those examples. So let us proceed. So for that, first we give some definitions and notations that we are going to use further. So from now onwards, we will call a graph G to be a gamma I graph if it satisfies the equality domination number equal to independent domination number. And what are private neighbors of a set? So for any subset S of the vertex set V and any vertex U in S, a vertex V is called a private neighbor of U with respect to S if U is the only point which belongs to the neighborhood of V and S. So NV intersection S should be equal to U. Then V will be called a private neighborhood of U. And if further we take V from V minus X, then V will be called an external private neighbor of U with respect to S. We denote the set of all private neighbors of U with respect to S by Pn of US, and the set of all external private neighbors of U with respect to V is denoted by Epn US. So suppose this is some set S and this is some U. So any vertex V which belongs to S and which is adjacent to only U will be called a private neighborhood of U with respect to S. And external private neighbor, if we take V from outside of U and if it is adjacent to only U, then it is called external private neighborhood of U with respect to S. So this private neighbor definition was given by Haynes, Hednemi and Slater, and it is there in the fundamental domination book. So motivated from the notion of private neighbor of a vertex set, we have introduced the concept of external private neighbor of a vertex as well as set. So this is the set of, so in this what we do, we take G to be a graph as any non-empty set, and we take for any pair UV belonging to S, the set UVS is the set of all vertices in V minus S such that NW intersection S is contained in UV, and it is called private neighbor set of UV with respect to S. And for our requirement, we have also defined these sets. If epsilon EPN star UV S means instead of containment, we have equality here, and then EPN US is the closed external private neighborhood of U and S. So that is, we are also taking U along with this external private neighborhood of US. So in this way, we have defined these sets for our requirement. And so this is the theorem which gives sufficient condition for a graph to satisfy the equality of domination number equal to independent domination number. So given any graph G, if it contains a gamma G set D such that for every gamma G set D dash satisfying this condition that the H set of the induced subgraph of D dash is contained in H set of the induced subgraph of D, and for each pair of adjacent vertices UV in D dash, the independent domination number of external private neighborhood closed external private neighborhood of UV with respect to D dash is equal to D2, then the domination number of that graph will be equal to its independent domination number.
Good.
So for example, let us take this graph G. So its domination number is 3. The vertices marked in this orange box, they dominate this set, dominate all the vertices outside D. And here D has only one pair of adjacent vertices. So U and V are on there is the only adjacent pair of vertices. And external private neighborhood of UV is W1, W2, W3. So if we take this, the induced subgraph of external private neighborhood of UV along with the set UV, then its independent domination number happens to be 2. And so it satisfies our sufficient condition. And hence for this graph, domination number is equal to independent domination number. So after giving this sufficient condition, we have also proved that the classical theorems that we mentioned earlier by theorems by Aaron and Nesker and other theorems present in the literature, some of the other theorems present in the literature happens to be corollary to our theorem. So if a graph has no induced subgraph isomorphic to the clock A13, then it satisfies our sufficient condition, and hence we can deduce that the domination number of such graphs will be equal to the independent domination number. And similarly, if we have a graph where the set of vertices of degree greater than equal to 3 is an independent dominating set, then again they satisfies our sufficient condition, and hence we can deduce that the domination number of such graphs will be equal to their independent domination number. So these two results are published in these two papers. Then we also prove that if a graph G has no induced subgraph isomorphic to one of these 16 graphs H1, H2, H16 given in top Walkman theorem, then such graphs will satisfy our sufficient condition, and consequently we can deduce the top Walkman theorem from our sufficient condition. So if a graph G has no induced subgraph isomorphic to one of the 16 graphs, then they happen to satisfy our sufficient condition, and therefore the domination number of such graphs is equal to the independent domination number. So here are some examples of graphs where our sufficient condition is satisfied, and hence we can say that these graphs satisfy the equality domination number equal to independent domination number, but these graphs does not satisfy the sufficient condition of Allen-Nesker theorem and top-Walkman theorem. So graph G1, it has claw and H1 as an induced subgraph. Then graph G2 has claw, H1, H2 up to H10 as an induced subgraph. And then graph G3, it has claw, H1 and H2 as an induced subgraph. So they all have an induced subgraph, so we cannot conclude anything about them from Allen-Nesker theorem and top-Walkman theorem, but they happen to satisfy our sufficient condition, and hence for them domination number is equal to independent domination number. So if we denote F1 the family of claw-free graphs, F2 the family of graphs which have no induced subgraph isomorphic to H1, H2 and H16, and if we denote F3 the family of graphs satisfying our sufficient condition, then F1 happens to be properly contained in F2 and F2 happens to be properly contained in F3. So with this we can say that our sufficient condition is a generalization of the classical theorems, top-Walkman theorem and Allen-Nesker theorem. So next we exhibit classes of gamma I graphs which belongs to F3, but they neither belongs to F1 nor they belongs to F2. So let us look at first such graph. So for that we have introduced the notion of, no, we have not introduced this. This is already there in the literature. So we have taken this generalized corona of a given graph. So a generalized corona of a graph is obtained by joining the ith vertex of G to all the vertices of Gi. And if I take any graph G of order P, and if I take H to be the graph obtained by generalized corona of G with KR1, KR complete graphs KR1, KR2 and KRP, then for this graph H, its domination number equals independent domination number, and it equals it and is equal to the cardinality of the vertex set, and this class satisfies our sufficient condition, but they have claw and some HIs as induced subgraph, as an induced subgraph. So for example, if I, yes, so this is an example. So this is C4 corona, K4, K3, K2, K2. So this is generalized corona graph. So I have a C4 0, 1, 2, 3, and then I have taken this K3. This is K3, and I have made this every vertex of this K3 adjacent to 1. Then this is K2. This is K2, and this is K4. So K4, K3, K2, K2. This is the generalized corona, and for this graph, G, its domination number is equal to independent domination number. Then Vaidya and Pandit, they defined duplication of an edge. So given any graph, G, we can obtain a graph H by duplicating an edge E equal to UV by a vertex, where the graph is obtained by a vertex by adding a vertex W such that UV is adjacent to W. So basically what we do in this duplication of an edge, so we have a graph, suppose this is a graph G and this is our edge UV. So what we do, duplication of edge E. So this is our edge E by vertex V is basically by vertex W is basically what we are doing. We are just adding W here and making it adjacent to both U and V. So this is our graph H obtained from G by duplicating edge E by the vertex W. So this is the definition given by Vaidya and Pandit in this paper. So then if I take any graph H obtained from G by duplication of each edge, instead of duplicating one edge, if we duplicate each edge of the graph by a new vertex, then it can be easily seen that H is the graph with vertex set VSG, where SG is the subdivision graph of G, and H set ESG union EG. So we are taking the H set of subdivision graph and along with H set of G, and thus H can be viewed in terms of subdivision graph of G, and we call H to be a duplicated subdivision graph of G. For example, let us take, so this is our G. So what we do, we take the subdivision. If we take the subdivision, so this will be a subdivision, this will be S of G, and then what we do, we take the original edges. So this was the original edge, this was the original edge, this was the original edge, and this was the original edge. So this will be our duplicated subdivision graph of G. So this is DS of C4. DS of C4. This is DS of C4, right? This graph. So if you can see, we are duplicating each edge exactly once by a new vertex. So this is DS of C4. So for such graphs, then we have proved that. So for any graph G, the graph with vertex at VSG and edge set ESG union EG is called duplicated subdivision graph of G, and it is denoted by DSG. So if I take any bipartite graph with bifurcation X and Y, such that cardinality of X is less than equal to Y, and if for such a graph there exists a matching M such that M saturates all the vertices of the vertex at X, then domination number of the duplicated subdivision graph of G will be equal to its independent domination number, and that will be equal to the cardinality of the partition X. Okay, so again this graph, it satisfies our sufficient condition, but it does not satisfy the condition of Analytical theorem and Top-Volkmann theorem. And the following result from Vaidya and others is an immediate consequence of the above theorem. So they have proved that for any complete graph, by complete bipartite graph, KRS, the domination number of duplicated subdivision graph of complete bipartite graph is equal to independent domination number of duplicated subdivision graph of KRS. So this can be directly obtained from the result, from this result. And we have other corollaries of the above result. So if G is any one factorable bipartite graph, then its domination number will be equal to independent domination number. And from the another very important fact that every regular bipartite graph admits a perfect matching. So we have this result that if G is a regular bipartite graph with bipartition XY, then its domination number of the duplicated subgraph of G will be equal to independent domination number of the duplicated subdivision graph of G.
Okay.
Okay. So then there was another definition given by Vedya and Pandit, and in that they define what they mean by duplicating a vertex by a new edge. So basically, what they do, they add a new edge and they make adjacent to both the vertices. So NHU is equal to WV and NHV is equal to WU. So motivated from this definition, we generalize this definition and we introduce that instead of taking an edge, because an edge is also K2. So instead of taking a K2, we can take any complete graph. So we define duplication of a vertex by a click. So this is the definition, that duplication of a vertex W by a click in a graph G produces a new graph G dash by adding click complete graph Kn such that Nu is equal to W union Vkn minus U for each U belonging to the vertex set of the complete graph Kn. And for that, we were able to prove that if we take any bipartite graph and we obtain H from G by duplicating each edge of G by a new vertex and also duplicating each vertex of G by some click, then the domination number of that graph H so obtained will be equal to its independent domination number, and which will be equal to the cardinality of the given graph G. So these are all the classes which belongs to F3, but they does not belongs to F1 union F2. And the result from Vedya and Pandit can be obtained from the above result. So Vedya and Pandit, they proved that for any given graph G, if we take the corona of the complete bipartite graph and we take the duplication of each edge of that, then the domination number will be equal to independent domination number. So this result can be obtained from the previous result, and we have another result that can be obtained from a previous result is this, that if G is a graph obtained by duplication of each edge of the cycle Cn by a new vertex and duplication of each vertex of Cn by some click, then the domination number will be equal to n, and independent domination number will be equal to n if n is even and n plus 1 if n is odd. So for even n, domination number will be equal to independent domination number. So these are my references. So these are some of the important papers on the parameter domination number equal to independent domination number. So those who are interested, they can refer these papers. Thank you.
Thank you, sir. Thank you.
Thank you, Professor Somiraj. So any questions?
Question from audience? Is there any question from audience? Students? Sir?
Yes.
Very nice presentation from the starting point and background references.
Thank you, sir. Thank you.
First, you are explaining chessboard with the Kuhn graph. Secondly, you are giving independent sum graph, independent and domination number
Yes,
are
I thought
not
that
equal, somewhere
students will also
equal.
be there. Students will also be listening to this talk, so I made it simpler and elementary also, so that they can understand this talk.
Sure, sir. Very
and they can
elementary
pursue,
explanation.
so they can pursue further research in this topic.
Variety of new classes of equal domination and independent domination, from 5-star to up to duplicating vertex or duplicating with the click graph. Very fine, sir. And you are giving the background references are very nice, sir. Very nice.
Thank you, sir. Thank you.
It's very much useful future work. If you follow your all work, definitely we will do some more results in your directions.
And
Thank you.
this topic has a very rich historical background also. So if anyone who pursues this research, this will be a very good research for them.
Sure, sir. Sure, sir. Audience, please, students. Any question from audience?
Sir, good morning, Rajesh sir.
Yes, ma'am.
I'm really more happy. Such a wonderful applications you have given graph theory here.
Thank you, ma'am. Thank you.
Initially, you was started slowly for the layman can easily understand what is graph, and
Yes,
finally you
because
ended with the
the students
weightage
were
of
also the, yes.
applications.
Yes, yes.
Really, it is a fantastic presentation about graph theory and dominance of graph theory and its application. I'm a topology person, but even though it is a very good applications in graph theory, I'm really more happy for seeing you such a wonderful application-oriented presentation, sir. Thank you, sir.
Thank you, ma'am. Thank you.
And now our students will come for vote of thanks, ma'am.
I would like to thank our honorable speaker, Dr. Rajesh sir, for visiting and enlightening us. Today's lecture was full of knowledge and interesting things. It gave deep insights into the topic and also revealed some interesting facts. I really enjoyed when you related our graph with the chessboard and the queen attack in it. And the comparison between domination and independent domination number had given me a lot of clarity between the both. Alan Lansker and Top-Walkman theorem was very interesting to hear with your words. And the definitions like private neighbors and the external private neighbors are really easy to understand when it comes from you, sir. All the corollaries, definitions, and theorem was really informative. It will definitely really helpful in our future. Once again, I would like to thank you, sir, Dr. Rajesh sir, for taking out time from your busy schedule and enlightening us with the knowledge. Thank you, sir.
Yes, thank you. And I would also like to once again thank Professor Solay Raju and others for giving me this opportunity to speak on this platform. So thank you, sir.
Thank you. Very nice, sir.
Thank you, sir.
Okay. So shall I stop sharing?
Yes, sir.
Yes, sir.
Okay.
Madam, அடுத்த section 2 o'clock.
Okay, sir. Will inform, sir.
2:51 அப்புறம் உங்க இது 3:15 to 4 ரெண்டு லெக்சர் இருக்கு. நான் அவருக்கு ஒரு மெசேஜ் போட்டு 2க்கு வரத மாதிரி பண்ணிக்கிறேன்.
Good afternoon to all. On behalf of Mother Teresa Women's University Department of Mathematics, we will conclude the session, and the next session will start at 2 o'clock in the same link. 2 to 3 is another resource person speech, and 3:15 to 4 o'clock and the third technical session. So please be in 2 o'clock in the same link. Thank you. Thank you very much for your presence in this session. Thank you, sir. Thank you, everyone.
கண்ணன் சார்.
எஸ் சார், எஸ் சார்.
சார் இது வரைக்கும் உள்ள ரெக்கார்டை க்ளோஸ் பண்ணி வச்சோம்.
ஷியர் சார். சார் லைவ்ல இருக்கும் சார். ஏன்னா யூடியூப் லைவ் இருக்கனால வந்து லைவ்ல இருக்கும். கேண்டிடேட் வந்து ரிமூவ் பண்ணிட்டு மறுபடியும் 2 o'clock ஜாயின் பண்ணிக்கலாம் சார்.
ஆடியபிள் மட்டும் நீங்க க்ளோஸ் பண்ணி வச்சுக்கோங்க.
எஸ் சார், க்ளோஸ் பண்ணிடுறேன்.
லைவ்ல லிங்க் இருக்கட்டும்.
எஸ் சார்.
நம்ம 145க்கு திரும்ப பேசிக்கலாம்.
எஸ். எஸ். Thank you.
Thank you. Thank you. Sir, Kannan sir. கண்ணன் சார்.
சார் சொல்லுங்க சார். ஹலோ சார். சார் கண்ணன் சார்.
ஹலோ ஹலோ, இந்த வர்றேன்.
எஸ்.
ஹலோ.
எஸ் சார்.
ரெண்டாவது டாக் ப்ரொஃபஸர் வந்து 1:45 மேல வரேன்னாரு.
ஓகே சார், ஷூர் சார்.
ஆமா, இந்த லாஸ்ட்ல மீட்டிங் முடிஞ்ச உடனே யாரோ எனக்கு ஃபோன் பண்ணாங்க.
ஓகே சார்.
இப்போ மைக் ஏதோ ஆன்ல இருந்துச்சா பாருங்க, அதை டெலிட் பண்ணிவிட்டு.
இல்ல சார், அதெல்லாம் நான் உங்களுக்கு எடிட் பண்ணி அனுப்பிச்சிடுவேன் சார், ஒன்றும் ப்ராப்ளம் இல்லை.
யாரோ மதர் தெரசா எனக்கு இதெல்லாம் அனுப்பல அதெல்லாம் அனுப்பலன்னு ஏன்ட்ட கேட்டுட்டு இருக்காங்க. நம்ம
இல்ல
பதில்
சார், அதெல்லாம்
சொல்லும்போது
வரல சார். இல்ல அதெல்லாம் வரல சார், வரல. ஏன்னா நான் மியூட்ல பாத்துட்டே இருந்தேன்ல, அதெல்லாம் நீங்க பேசுனதுல வரல.
எனக்கு ஃபோன் வருதுல, அது கேக்குமா? ஃபோன் வருதுல.
ஃபோன் வருதா? கேட்காது சார்.
இப்போ நான் வந்து ஆடியபிளா இருக்கேன், ஃபோன் வருது. ஃபோன்ல நான் பேசுறது அங்க பதிவாகுமா?
இல்ல, ஆகாதுங்க சார்.
ஆகாது. ஏன்னா சில பேர் லிங்க் கேட்டு துன்புறுத்திட்டே இருந்தாங்க.
சரிங்க சார், சரிங்க சார்.
அவங்களுக்கு மெயில் பார்க்காம என்கிட்ட அவங்க இதை செய்யல அதை செய்யல அப்படின்னாங்க, அதுதான் கேட்டேன்.
ஓ சரிங்க சார், சரிங்க சார், சரிங்க சார்.
அதெல்லாம் பதிஞ்சு அவங்க வருத்தப்படுவாங்க இல்லையா?
யூடியூப் லிங்க்ல பார்த்தா சொல்லிடுங்க சார். இல்லைன்னா
யூடியூப்ல இருந்தாலும் அதை டெலிட் பண்ணிக்கலாம்.
எஸ் சார்.
ஆடியோபிள் இருந்தா அவங்க காதுக்கு போகல, அதுக்காக.
எஸ் சார்.
ஏன்னா அவங்களும் ஆடியோபிளா இருப்பாங்க பேசும்போது. அந்த மாதிரி இப்போ ஃபோன்ல இப்போ நான் இப்போ உங்கள்கிட்ட வீடியோல பேசிட்டு இருக்கேன். இதுவே எனக்கு ஃபோன் வருது, ஃபோன் ரெக்கார்ட் ஆகுமா?
சார், ஃபோன் வந்து உங்களுக்கு ஃபோன்ல ரெக்கார்ட் ஆகாதுங்க சார். இது டெஸ்க்டாப்ல மட்டும் தான் சார் ரெக்கார்ட் ஆகும்.
உங்க இதுல ஆகும்?
ஆமாங்க சார், என்னோட சிஸ்டர் லோக்கல்ல ஆகும் சார். இப்போ நான் உங்களுக்கு பெர்மிஷன் கொடுத்துருக்கேன் சார். நான் உங்களுக்கு பெர்மிஷன் கொடுத்துருக்கனால நீங்க உங்களோட டெஸ்க்டாப்ல இப்போ ஓபன் பண்ணீங்கன்னா அதை ரெக்கார்ட் பண்ணிக்கலாம்.
ரைட்டு. இப்போ எனக்கு ஒரு ஃபோன் வருதுன்னு வச்சுக்கோங்க, நீங்க கேட்க முடியுமா அதை?
அது நீங்க இப்போ ஃபோன், ஏன்னா நீங்க அதே ஃபோன்ல தானே சார் இருப்பீங்க, அதனால கேட்காங்க சார். உங்களுக்கு பக்கத்துல இன்னொரு ஃபோன் இருந்துச்சுன்னா அது எனக்கு கேட்கும்.
நிச்சயமா இதே ஃபோன் தான் கேட்காது. அவங்க தான் ஒருத்தவங்க பேசிருக்கப்ப டக்குன்னு ஒரு வார்த்தையை விட்டாங்க, கட்ட வார்த்தை. பதிஞ்சா தப்பு இல்லையா, அதனால கேட்டுக்கிட்டு.
ஓ சரி.
என்னங்க அது அப்படின்னு ஒரு மாதிரி.
ஏன்னா இப்ப நீங்க சப்போஸ் அப்படியே வந்து வாய்ஸ் வந்தாலும் நான் இங்க மீட் பண்ணிடுவேன் சார் உங்களோடத.
ஆமா கரெக்ட்.
நான் இங்க எல்லாத்தையும் மீட் அதுதான் பார்த்துட்டே இருப்பேன்ல சார்.
இல்ல அவங்க போன்ல தான் பேசுனாங்க, வீடியோல வரல. இதே போன்.
சரிங்க சார், சரிங்க சார். சார் நீங்க நார்மல் கால் வந்துறீங்களா சார்?
நார்மல் காலா?
நார்மல் கால் வரீங்களா?
வர்றேன்.
எஸ்.
Amaravati. Naviyan ஒருத்தன் chief guest. கண்ணன் ரெடியா இருக்கீங்களா?
சார் ரெடி சார்.
இருக்கீங்களா?
எஸ் சார்.
அவர் 150 வருவேன்னாரு.
வரட்டும் சார், நோ ப்ராப்ளம்.
வந்துட்டாருன்னா பிரச்சனை இல்லை, இன்ட்ரோடக்ஷன் பண்ணிட்டு ஆரம்பிச்சிடலாம்.
எஸ் சார், ஷூர்.
அவர் 150 வந்தாலும் 155 வச்சுட்டு இன்ட்ரோடக்ஷன் பண்ணிட்டு 2 o'clock அவர் பேசுற மாதிரி பண்ணிக்க முடியும்.
ஷியோர் சார். எஸ் சார். எஸ் சார்.
சாப்பிட்டீங்களா?
இல்ல இனிமேல் தான் சார்.
ஆரம்பிச்சு விட்டு சாப்பிடணுமா?
எஸ் சார். அப்படியே பேரலா சார். இங்கே தான் அப்படியே தான் சாப்பிடணும். ஸ்பூன்ல தான்.
ஓ சரி சரி. நானும் சாப்பிடல, ஆரம்பிச்சுட்டு ஒரு கிளாஸ் இருக்கு ஆன்லைன்.
ஓ சரிங்க சார். சரிங்க சார்.
2:30க்கு 3க்கு தான் மேலதான் சாப்பிட முடியும்.
சரிங்க சார்.
அவர் அப்பெல்லாம் ஃபோன் பண்ணிட்டு பார்க்கலாம்.
சரிங்க சார். சரிங்க சார்.
அவர் லிங்க்ல வந்தாருன்னா உடனே சொல்லிருங்க என்கிட்ட.
ஓகே சார். கண்டிப்பா சார்.
சரி ஆஃப் பண்ணுங்க. என்னாச்சுன்னு பாருங்க. விமலா மேடம், விமலா மேடம், புவனேஸ்வர் மேடம், No. இப்ப கேக்குதா விமலா மேடம்? மேடம் இப்ப கேக்குதா? விமலா மேடம் ரெடியா?
Hello.
Sir, சொல்லுங்க sir.
Hello. Are you able to listen me?
Yes sir, we are able to hear your voice sir.
Okay, I will try to make the presentation.
Yes sir.
Good afternoon, Professor.
Good afternoon. How are you?
Fine, sir.
I'm trying to connect my presentation.
I arrange and come after introduction with you. After the introduction about you, we will start.
Yeah, first of all, I'll see I'm able to share my screen.
Yes, sir. We can screen. We are able to see your screen, sir.
Okay, so you are able to see the presentation?
Yes, sir. Presentation is visible, sir, but your video is not visible, sir.
Okay, my video is not visible. Just
Yes,
a
sir.
minute. Okay, so
yes, sir. Now visible, sir. Yeah, just to.
HOD madam. கண்ணன் சார் இன்ட்ரோடக்ஷன் ஆரம்பிக்கிறதுக்கு இன்ஸ்ட்ரக்ஷன் கொடுக்கணும். விமலா இருக்காங்களா இல்ல மேடம் இருக்காங்களா கொஞ்சம் சொல்லுங்க. கண்ணன் சார்.
சார் விமலா மேடம் இருக்காங்க சார்.
கண்ணன் சார்.
சார். ஹலோ.
இன்ட்ரோடக்ஷன் ஆரம்பிக்கிறதுக்கு யார் அவைலபிள் பாருங்க.
சார் விமலா மேடம் இருக்காங்க சார்.
விமலா மேடம் இருக்காங்களா இல்ல?
இருக்காங்க சார், இருக்காங்க சார். அப்புறம்
சரி, அவங்களுக்கு அப்போ மூட் ரிலீஸ் பண்ணுங்க, நான் அவங்ககிட்ட சொல்லிடுறேன்.
எஸ் சார், அவங்க அன்மியூட் பண்ணி தான் சார் இருக்காங்க. நவ யூ கேன் டாக் சார்.
அன்மியூட்ல இருக்கா?
எஸ் சார், பேசுங்க.
சரி, அவங்க வீடியோ ஆன் பண்ண சொல்லிட்டு. விமலா மேடம். விமலா மேடம்.
சார் குட் ஆஃப்டர்நூன் டு ஆல்.
நீங்க இன்ட்ரோடக்ஷன் ஆரம்பிக்கணும் மேடம்.
விமல்
மேடம். எஸ் மேடம், ஹெச்ஓடி மேடம். மேடம் இன்ட்ரோடக்ஷன் ஆரம்பிச்சிடலாம், சார் வந்துட்டாரு.
ஓகே, விமலா, டாக்டர் விமலா. Professor, most welcome to Mother Teresa Women's University Mathematics Department. Imala ma'am, student join, ask them to join immediately.
An equation means nothing to me unless it expresses a thought of God, by Srinivasa Ramanujan. Wishing you a splendid afternoon to one and all present here. Half of the day is over. We are gathered here for our next session of 3 days of international webinar on applied mathematics organized by Department of Mathematics, Mother Teresa Women's University, Kodaikanal. It's my pleasure to welcome Dr. Pizada sir, Assistant Professor, Department of Mathematics, University of Kashmir. Welcome, sir. Now I request Ms. Navya to give a deliverance about our honorable speaker, Dr. S. Pizada sir.
A very pleasant good morning to one and all gathered here. It's great pleasure for me to introduce our respected Professor Dr. Sarfudian Prizada, Professor and Head in Mathematics, Department of Mathematics, University of Kashmir. Professor received PhD and MPhil degrees in Applied Mathematics from AM University, postgraduate degree in Mathematics at University of Kashmir. Professor render his service in many institutions like Kingford University of Petroleum and Minerals, National Institute of Technology, Degree College, Paramula in and around Kashmir. Sir, research area of interest are graph theory, theoretical computer science, and algebra. He acted administrative position or dean, School of Physical and Mathematical Science. Under his guidance, 6 PhD and 4 MPhils were completed. Professor received grants from ICIAM, SERP DST, ICM 2018, NPHM, Gley Mathematical Institute, Center for Interdisciplinary Research, Germany, Hungarian Scholarship Board, ICTP, IPM, DSR, Kingford University of Petroleum and Minerals for conference. He is visiting fellow of Nanjing University, China. Professor received Young Scientist Award from Science and Technology, J&K Government, India. Professor written 2 books under the title of Comparison-Based Ranking in Algorithm of Informatics and Scores Set Kings in Oriented Graphs in Algorithm of Informatics. Professor complete 4 major projects. Professor have 7 international research collaborations. Apart from the research, professor is editorial board member of European Journal of Pure and Applied Mathematics, Discrete Mathematics Letters. Professor is member of following professor bodies are American Mathematical Society, Indian Mathematical Society, Advanced in Discrete Mathematics and Applications, Research Group in Mathematical Inequalities and Applications, RIGMA, Australia. Professor organized 3 national and international programs. Behalf of our Ramanujam Club activity, Department of Mathematics, Mother Teresa University, Kodaikanal. Welcome you, sir.
Thank you.
Thank you, Ms. Navya. I consider it a great honor to welcome our chief guest, Dr. S. Pizzada, sir.
Thank you very much for your kind words, and thank you for the invitation to speak over here and exchange my research ideas with you and various other participants. So I hope you are able to see my presentation.
Yes, sir. No problem.
Okay, so are you able to see the
Yes, sir.
presentation?
We are able to see you.
Okay, so I should continue. Okay. So my talk will be about the Laplacian eigenvalues of a graph. And in this case,
Excuse me, sir, your screen is not visible, sir.
my screen is not visible. That's
Yes.
what I was pointing out.
Yes.
Okay, is it now visible?
Not yet coming, sir.
It's coming now.
No, sir.
Okay.
Yeah, now visible, sir.
Okay.
Yes.
So as I said, that my talk will be about the Laplacian eigenvalues of a graph. This is one of the areas included in the
Okay,
spectral
screen
graph
visible.
theory. So what we mean by spectral graph theory is the association of matrices to graphs. Rather, we can say when it becomes sometimes difficult to work on graphs, especially large graphs with the order being very high and the size being very high, difficult to store in the computer. So we use various representations for the graphs. And one such algebraic representation is the use of matrices. And in this spectral graph theory, once we represent a graph by a matrix, then we deal with the linear algebraic properties such as the characteristic equation, the eigenvalues problem, the eigenvectors problem, and so many other spectral problems. Now the question is, how many matrices do there exist? There exist many matrices which have been associated with a graph. For example, the incidence matrix, the adjacency matrix, the cycle matrix, and so many other matrices, and newer matrices also being uh, located now. People see work on graphs, and then they try to find the newer matrices. The matrix like 5-6 years old or so, distance matrix based on the distance of the vertices in the graph. So how these matrices differ from each other, it is the parameter which we use while constructing such a matrix. It's like just now I said distance matrix, so it means the distance between two vertices are involved. Or the adjacency matrix, it means whenever the two vertices are adjacent or not. So the ijth elements of these matrices depend on the variable or the parameter we use while defining these matrices. For my talk today, I will be dealing with one such matrix which is called as the Laplacian matrix of a graph. And later on, I will introduce some interesting problems, interesting conjectures, and the development of such conjectures. So let's start with the adjacency matrix. Now, this adjacency matrix is a square matrix whose order is n, where n is the order of the graph, and its ijth element is 1 or 0, according as there is an edge between a vertex vi and vj. So this matrix is a binary matrix. Its values are ijth values are 0 or 1. So 1 when the two vertices are adjacent and 0 otherwise. Imagine we have a graph, and how we form this matrix. We take the rows as the vertices and the columns as the vertices. So the columns will be named by the vertices like v1, v2, so on to vn, and the columns will be again named by the same vertices v as the vertices vn. Now the first entry will be intersection of v1 and v1, so it's 0. Similarly, the intersection of v1 and v2 means if there is an edge between v1 and v2, we put it 1, otherwise 0. So briefly speaking, that this is a binary matrix, or we call it also as a 0-1 matrix. And about this adjacency matrix, once we have this square matrix, adjacency matrix, we can find the characteristic equation of this matrix. And once we have the characteristic equation, we have the roots of that characteristic equation, which we call as the eigenvalues of the adjacency matrix. And the set of all eigenvalues with their multiplicities, meaning if the eigenvalue is repeated, we call it as the spectrum of the adjacency matrix, or simply in graph theoretical terms, it's called as spectrum of the graph. And this area has been researched for quite long now, 30-40 years, this spectral properties of the graph, where we deal with the eigenvalues, and then we try to find so many connections in day-to-day life problems. And in fact, there are many applications of this spectral properties of the graph. Okay, we move forward, which is the main issue of our talk, that is the Laplacian matrix of a graph. So here is the definition. This matrix is a combinatorial definition here. It's again an n by n matrix, where now we have the ijth element. It has 3 possibilities. If there is an edge between two vertices, we put the value as -1, the diagonal elements as the degree of the vertices. Remember that in adjacency matrix, the diagonal elements were all zeros, but here we include the values of the degrees of the vertices and put them along the diagonal elements. And if the two vertices are not adjacent, then the value is 0. So it's either -1 or di. So diagonal elements are di and non-diagonal elements are -1 and 0. So D, as I said, these are the diagonal elements. So we have here. Alternatively, this Laplacian matrix can be defined as the diagonal matrix minus the adjacency matrix. Now, just imagine the diagonal matrix is the matrix, square matrix, whose all diagonal elements are the degrees and non-diagonal elements are zeros. So it is D1, D2, and so on, Dn along the main diagonal. Other elements are zeros. And adjacency matrix just defined. It's a binary matrix. So when we subtract these two, it will give the older version of this Laplacian matrix, which we defined just in the previous slide. That is -1, D, I, and 0. So, okay, so now we take this as, okay. Now for this Laplacian matrix, once again, as I earlier said, that we'll be interested in the characteristic equation and the roots of that characteristic equation, which is our spectra. In the adjacency matrix, the spectra was just called as spectra or spectrum or the spectrum of the adjacency matrix. And here we have the eigenvalues of this Laplacian matrix, the eigenvalues of this Laplacian matrix, and the eigenvalues, the set of all eigenvalues will be called as spectra or Laplacian spectrum. This will be our focus, spectrum or the Laplacian spectrum of G. Okay, this Laplacian matrix is always a real symmetric. It is positive semi-definite and it's singular. Since it's real symmetric, the Laplacian spectrum is real, one eigenvalue 0. Means these things have all been proved. They are been verified earlier that the eigenvalues of this Laplacian matrix are always real, and it has always one eigenvalue as 0. So we introduce some notations. Imagine that mu1, mu2, so on to mu_n, where mu1 is bigger or equal to mu2 and so on, be the Laplacian eigenvalues. And the last one, the smallest one, is always 0. This is true for any graph. Choose any graph, form the Laplacian matrix, the smallest eigenvalue will be always 0. So if we find the sum of all these Laplacian eigenvalues, that's mu1 plus mu2, so on to mu_n, it always equals the trace of this Laplacian matrix, which in fact is the sum of the degrees, and the sum of the degrees of a graph is always twice m. So the sum of the Laplacian eigenvalues, that's mu1 plus mu2 plus so on to mu_n, is always twice m. So this is something like we say we are trying to find connections between the Laplacian eigenvalues and the graph structure. Okay. In books, we also see in undergraduate courses or master's courses, when we deal with this graph theory, we call this matrix as the Kirchhoff matrix, because it has a master's as the Kirchhoff matrix, is attributed to Kirchhoff. So there are other names for this matrix. Since it's used in electrical networks, its name is matrix of admittance. And lastly, we take another form of this Laplacian matrix. Before I take the other form of this Laplacian matrix, we note that as there are several applications of the adjacency matrix for the real-time problems, day-to-day problems, similarly, these other matrices where we have started Laplacian matrix also finds useful applications. So imagine we have a graph, any graph, finite graph, and what we do, we orient the edges arbitrarily. That is, we try to make it as a directed graph. So once we give the orientation, any edge given as the positive edge, and similarly we orient all the edges. Once it becomes an oriented graph or the directed graph, then we form a matrix which is called as matrix C. Now, this C matrix is of order n by m. So it has n rows and m columns. Unlike the older matrices like the adjacency matrix and the Laplacian matrix, which we defined earlier, they were square matrices. But this matrix C, as you can see here, it's not a square matrix. It's n by m. Means the rows are number of rows is n and the number of columns is m. And the ijth element is 1, minus 1, or 0, according as jth edge is incident on ith vertex, jth edge is incident from ith vertex. Like I said that when you make a graph to be a directed graph, when you give a direction to the edge, it becomes an arc. So we have outgoing arcs and incoming arcs at a particular vertex. So if there is an arc which is outgoing at a vertex, we put +1. And if there is an arc which is incoming arc, it's -1. And if there's no arc at all, it is 0. So this is matrix C. Now take the transpose of this C. When we take the transpose of the C and then we multiply C and C transpose, here you see it's C and C transpose. Whatever is the result is a square matrix, and it has been found to be our Laplacian matrix. So we can say the Laplacian matrix can also be defined as the product of the matrix C and the transpose of this matrix C. What C? C is the matrix here. So as I said that this mu and the smallest eigenvalue, Laplacian eigenvalue 0, and the multiplicity is equal to the number of connected components of G. Now the question was how many eigenvalues will be 0. We said that the smallest is 0. It's a guarantee that one eigenvalue is 0, but how many Laplacian eigenvalues will be 0? So it was settled by Fielder in 1973 when he said that the number of eigenvalues which are 0 depends on the components of the graph. That means if a graph is disconnected and has 5 components, for example, it will definitely have 5 Laplacian eigenvalues whose value is 0. Not only that, Fiedler also showed that G is connected if and only if the second smallest eigenvalue is positive, and call it as algebraic connectivity of the graph. Very important concept in this spectral graph theory and the connectivity of the graph. So if we are asked to find the connectivity of the graph is connected or not, we just find the second smallest eigenvalue. If it is positive, the graph will be connected, which is the meaning of this observation. So it is necessary as well as sufficient. So if a graph is connected, then second smallest Laplacian eigenvalue is always positive and vice versa. So what was the connection of Kirchhoff? When we said that it's also called as Kirchhoff matrix. So imagine we have a connected graph G whose order is n. We know by matrix tree theorem the cofactors of the matrix LG are equal. All the cofactors are same. So if we form the Laplacian matrix and we form the cofactors of this LG, they are same, and each cofactor is equal to the number of spanning trees in G. That means it gives the complexity of the graph. If we have a connected graph, the number of spanning trees in a connected graph is called the complexity. And this complexity is calculated by Laplacian matrix. In fact, it was found in 1847. But at that point of time, it was used only for finding the number of spanning trees. and other spectral properties came later on. So let's take the complement of the graph, which we denote by G bar. Now, what's the complement of a graph? It is the graph obtained from the original graph with the same vertex and taking the edge which is not present in the original graph. So if we have K3, like the cycle of length 3, all the edges are there, and the complement with these 3 vertices will be the empty graph. Or any complete graph, its complement is the empty graph. So by certain linear algebraic techniques, we find the Laplacian eigenvalues of this G complement, and they are 0, n minus mu1, n minus mu n minus 1 in non-decreasing order. Now, why I mention this eigenvalues of complement? Because sometimes it will be very difficult to calculate the eigenvalues of the graph. And what we do there, we form the complement of the graph. Once we have the complement of the graph, and then we can make a connection between the spectrum of the original graph. Secondly, if G is a graph with connected components Gi, so the graph G is disconnected, having components Gi, like G, and Laplacian spectrum of G is the union of these Laplacian spectra and the spectra. So for union, it's easier. We take the spectra of all those graphs, that will be the spectrum of the union. Okay, let's come to complete graph Kn. It is a graph with every possible edge and is denoted by Kn. By certain calculations, we see that the Laplacian spectrum is n minus 1. So this is actually not the power. This is the multiplicity of the Laplacian eigenvalue, how many times this eigenvalue is repeated. So it means there are n minus 1 eigenvalues whose value is n. So n occurs n minus 1 times. And as said, one Laplacian eigenvalue is always 0. Okay, take the complement of this, all the eigenvalues will be 0. Similarly, we can see for the complete bipartite graph, the complete bipartite graph is denoted by K suffix mn. It is defined as a graph whose vertex set can be partitioned into 2 parts. For example, say V1 and V2, so that every possible edge is between a vertex in V1 to a vertex in V2. That's our bipartite graph. And if there is every possible edge present in the graph, then it's complete. And its complement will be denoted by K bar. And then you can see this K bar Mn is also a disjoint union of Km and Kn. Now we can imagine the complete bipartite graph. The edges, all the edges are between V1 and V2. And if we take the complement, these edges will disappear. And in the complement, the edges will come from within Vn, which was earlier the independent set. And the edges will come from within V2, which again was an independent set. That's why we have written here that this complement of the complete bipartite graph is always the disjoint union of Km, Kn. Okay, what about the Laplacian eigenvalues of the complement? It's given by this n occurring n minus 1 times, m occurring m minus 1 times, and 0 occurring twice. With the help of these Laplacian eigenvalues, we can be able to find the Laplacian eigenvalues of this Kmn. They are m plus n is 1 time, n is m minus 1 times, m is n minus 1 times, and there is one Laplacian eigenvalue, which is 0. We note that there is a strong connection between the diameter of a graph and the number of distinct eigenvalues of a graph. There's a connection like the given a graph with certain diameter, we can say some information about distinct eigenvalues of a graph. So we have this in the form of this theorem, which says that if a graph has diameter d, then there are d plus 1 distinct eigenvalues. Not only distinct eigenvalues, but Laplacian eigenvalues and signless Laplacian eigenvalues, which I come in the last stage. So let's forget about these signless Laplacian eigenvalues for the time being. So, but this theorem is so strong that it holds in all the three forms of the matrices. That is the adjacency matrix, there are d plus 1 distinct eigenvalues. For the Laplacian matrix, there are d plus 1 Laplacian eigenvalues, and for the signless also. Let's come to Laplacian integral graphs. Now, when we find the roots of the characteristic equation, we say that they are the Laplacian eigenvalues and they are all real, but nothing can guarantee whether they are integers or not. If all the Laplacian eigenvalues are integers, then we can say the spectrum is integral, which means all the Laplacian eigenvalues are integers. And this throws a light on the graph. So we call that graph as Laplacian integral graph. So here we have written Laplacian integral graph. It's that graph whose Laplacian spectrum consists of integers only. We know the following observations. If G is Laplacian integral, then so is G complement. Well, we know that a star graph is always a tree. The star graph is a tree with a common vertex, and there is a stable set, like it's in the form of K1D. Like here, it's like this, like this, like this. So similarly, we can define K1N. So there is one vertex which is joined to all other vertices. All other vertices are pendant vertices. For this star, there is a necessary and sufficient condition for a tree to be Laplacian integral. When a tree is Laplacian integral, a tree is Laplacian integral if and only if it is a star. That means among the family of trees, all trees, the star is always Laplacian integral. Means the graphs of this type, K1D, their spectrum is all integral. We have some types of graphs here, like you can see Gn is a graph obtained by subdividing one edge. So subdivision means we replace one edge, put a vertex in that edge, so that this original edge will be now two edges. So we have this Gn is the graph obtained from G, or is the graph obtained from subdividing one edge of Kn minus 1. So here if we choose Kn minus 1, we take one edge, subdivide it to get Gn. And we have found out that this Gn is always Laplacian integral because its complement is also Laplacian integral. It has two connected components, K2 and K1 n minus 3. This is Laplacian integral because it is a star graph. This is Laplacian integral. So the union is also Laplacian integral. Therefore, this Gn is Laplacian integral. Similarly, if Sg is another graph formed from G by subdividing every edge, then Groen and Maris in 94 observed the following. This Sg is Laplacian integral if and only if G is the graph Kn, or in other words, it's isomorphic to Kn. So this is only possible. Sg is Laplacian integral only when this G is Kn. Well, now take an example of a graph in which there is no P4 as an induced subgraph. So imagine there's a graph and it does not contain induced subgraph as the path of length 4. We call such graphs as cographs. Obviously, K1 is a cograph. Further, if G is a cograph, then the complement is also the cograph. And if there are two cographs, their union is a cograph. And we observe that the spectrum of cograph is always Laplacian integral. I'm putting these basic things in order to build a stronger theory. So a stronger conjecture and stronger problems. All these types of graphs and these basic things about the Laplacian spectrum are required in settling those cases. Well, we have this graph which is called as the split graph. So the definition is G is a split graph. Its vertex set can be partitioned into two parts like here. One part is here and another part is here. One part is a complete graph. Another part is totally disconnected. And we have edges between some vertices here and some vertices here. If this is possible for a graph, this partitioning is possible for a graph, then we say the graph is a split graph. A precaution, every graph cannot be a split graph. So this is not always true that this partitioning exists. Further, if the partitioning contains all these edges, like you have dotted edges here, if these dotted edges are from every vertex of K to every vertex of S, then it is called a complete split graph. So this KS is referred as the split partition, and it's always denoted by GKS. It's also called the polar graph. The complement of a split graph is always split. Every induced subgraph of a split graph is a split graph. And then one more important type of graph, which is mostly used in spectral graph theory, that is the threshold graph. It has no induced subgraph, which is isomorphic to path of length 4 or cycle of length 4 or twice K2. K2 means the single edge. It's also called degree maximal graph. This graph can be created recursively by means of two operations. We can construct a graph, this threshold graph, as follows. So what we do, add a dominating vertex adjacent to all previous vertices in the construction, or add an isolated vertex, isolated from all previous vertices. So every stage when we have this, we start with an empty graph, we start with a vertex, single vertex. Then for this single vertex, add a dominating vertex or an isolated vertex, and continue this process. The resulting graph will be a threshold graph. Okay, we take some techniques from this linear algebra. There are several techniques which will be often used in our graph theory. The first one is the majorization technique, where we take two sequences which are real, say they are of length n, then one sequence majorizes the second sequence if this condition is true, that is summation of xi is less or equal to summation of yi for all t lying between 1 and n. N is excluded here, and the equality holds when it's up to n, when t is equal to n. And this, the spectrum of Laplace matrix or the Laplacian matrix and this majorization technique, they have a strong connection. Now then we have the interlacing situation. When one sequence interlaces the second sequence, we take once again two sequences of real numbers. The second sequence is said to interlace the first sequence if these conditions are true, conditions given by number 2 here. And this interlacing is tight if the conditions are in the following form. So we have this set of conditions given by 3. So, well, related to majorization theory, we have Schur's inequality. We do it in the advanced matrix theory, Schur's inequality. It says that if A is a real symmetric matrix with eigenvalues lambda 1, lambda 2 to lambda n, and diagonal elements d1, d2 to dn, then summation of this is less or equal to summation of this eigenvalues. That means the diagonal elements majorize the spectrum. It's true for all t between 1 and n. This is Schur's inequality. A is a symmetric matrix whose diagonal elements are d1, d2, dn. It's any matrix, but should be real and symmetric. And its Laplacian eigenvalues, sorry, this is eigenvalues here only because this is true for this matrix where lambda 1, lambda 2 are the eigenvalues of the matrix. Okay, let's now take this D to be the degree sequence of G. Well, degree of a vertex is the number of edges incident on a vertex, and if we take all the degrees, it forms a degree sequence. We put them in certain order. Here it is like, here it is in the non-increasing order, so D1 is bigger or equal to D2 and so on. And we form a conjugate degree sequence where conjugate degree D star is defined by this sequence, and each dk is the cardinality of the set I, where di is bigger or equal to k. So from a given degree sequence, we have a graph G, we can find the degrees, we can find the degree sequence, and from this degree sequence, we find the conjugate degrees. Note this example. Suppose we have this D as the degree sequence of a graph, and well, D star is the conjugate degree sequence is given by this. So this D is the partition of the integer di, then D star is the conjugate partition. So just a notation, if D is the partition of this sequence, then D star is the partition of this sequence. Applying Schur's theorem, we see that this degree sequence is measured by the spectrum, Laplacian spectrum mu. The degree sequence of a graph is measured by its conjugate degree sequence. This can be seen easily from the theorem below. So this theorem says that the degree sequence is measured by the conjugate degree sequence. Here the degree sequence is measured by the Laplacian spectrum. So two observations. One observation is the degree sequence is measured by conjugate degree sequence, and the second observation from Schur's theorem, degree sequence is measured by the Laplacian spectrum. And when we consider these two, now take this di star here, graph theoretically, where V belongs to the vertex set, so the degree of V is bigger or equal to I, its cardinality, and we denote the sum of k largest Laplacian eigenvalues of G by skg. Well, we have to remember this skg for rest of the talk, because most of the things we deal with this skg, and this skg we define as the sum of k largest Laplacian eigenvalues. Recall that we denoted the Laplacian eigenvalues by mu1, mu2, and so on, where mu1 was bigger or equal to mu2, and the lowest one was 0. So we take the sum of k largest Laplacian eigenvalues. So from Schur's inequality, the Laplacian spectrum measurizes the degree sequence, earlier said. And if we apply Gale-Reiser theorem, conjugate degree sequence measurizes degree sequence. And it was in 1994, Braun and Maris raised the natural question whether the Laplacian spectrum and the conjugate degree sequence are measurization comparable. That means here in the previous slide, Laplacian spectrum measurizes degree sequence, conjugate degree sequence measurizes degree sequence. Braun and Maris raised the question as Laplacian spectrum and conjugate degree sequence are measurization comparable. And this was the observation made by Braun and Maris, which is now called as Braun-Maris theorem. It says that this skg is always less or equal to summation. This is the conjugate degree sequence, so they are measurization comparable, and the proof of this result came much later in 2011 or so. It was given by Bai. So this was, before this, it was just a conjecture up to 2011. So from 1994 to 2011, it was a conjecture, and it was proved in 2011, which appeared in Transactions, American Mathematical Society. Well, now, analogs to this Braun-Maris theorem, Brouwer in 2012 conjectured the following. So this is what Brouwer conjectured. If G is a graph with n vertices and m edges, then for any k, this skg, that is the sum of the k largest Laplacian eigenvalues, is always smaller or equal to m plus k plus 1 choose 2. Very interesting conjecture. Well, for all the researchers, this conjecture is still open, although a lot of progress has been made towards this direction, but still the conjecture has not been fully settled. It has been proved for various families of graphs depending on certain graph parameters. And the problem in settling this conjecture is this right hand side. In other words, this is the upper bound for the sum of k largest Laplacian eigenvalues. The problem here is that the right hand side is only in terms of one parameter, that's m, which is the size of the graph. This k is not a parameter because it is k here. It is the summation of k largest Laplacian eigenvalues, so it can vary according to the problem. In fact, the whole quantity depends on this m. This is what makes it little harder since only one parameter is given. So this is the first problem which we can discuss and which still is open. Now about this problem, there are various techniques used by graph theorists from time to time. One such technique is that we try to get this SKG, that summation, in terms of more than one parameter. If it is only one parameter here, we get bounds, upper bounds in certain other parameters. And finally, if we are able to eliminate other parameters and make the conclusion in terms of this ebb only, means that we are going in the right direction. So these are some developments of this conjecture. By computer calculations, Brouwer checked this conjecture for all graphs with 10 vertices. So we don't need to check those smaller graphs with 10 vertices. That conjecture is true. When k equal to n or n minus 1, since the sum of the all Laplacian eigenvalues is 2m, so it's true here also. If k is 1, it's true here also. Now, this Brouwer's conjecture, sometimes I will denote by BC. It holds for regular graphs. It has been proved, so we don't need to check for regular graphs. Hammer's Mohammedian and Taifeh in 2012 proved that this is true for all graphs when k is equal to 2. That means sum of two largest eigenvalues is always bounded above by that quantity which was Brouwer's conjecture. So this is true for all graphs when k is equal to 2, means every graph has been settled when k is equal to 2. It's true for all trees. And further observations, if G satisfies Brouwer's inequality, then G complement also satisfies this Brouwer's inequality. That means Brouwer's conjecture is true. Similarly, if H and G are two graphs which satisfy Brouwer's inequality, their union also satisfies Brouwer's conjecture. Brouwer's conjecture is true for co-graphs. Remember, we discussed this earlier about the definition of Brouwer's conjecture. Is true for these co-graphs. So co-graphs, for co-graphs, Brouwer's conjecture is true. Brouwer's conjecture is true for k-partite graphs. This is the extension of bipartite graphs. And these k-partite graphs are nothing but as complete k-partite graphs are co-graphs. So k-partite graph is a family of co-graphs. So when the conjecture is true for co-graphs, it's true for k-partite graphs also. In 2011, there was some progress made on the k largest Laplacian eigenvalue by Fischer, Hoppen, Rocha, and Teresa. It's in 2011, and they proved for trees that the sum of k largest Laplacian eigenvalues for a tree is this one. You see, this is not Brouwer's conjecture here, but this can be reduced to Brouwer's conjecture, as you can see in 2012, Du and Zhu obtained various bounds for SKG then proved that this Brouwer's conjecture is true for unicyclic and bicyclic graph. This unicyclic and bicyclic graphs, they are also important classes of graphs. Unicyclic graph means a graph containing only one cycle, and if a graph has two cycles, those graphs are bicyclic graphs. Rocha and Trevisan also made some progress, proved the Brouwer's conjecture for certain families of graphs, which are here. So they tried to obtain the sum of k largest Laplacian eigenvalues in terms of the girth, G. G is the girth, which is the length of the smallest cycle, and delta is the largest degree, maximum degree in the graph. Well, let's define a clique. What is a clique? The maximum complete subgraph of a clique is the clique of a graph, and the cardinality of this maximum clique is the clique number, which we denote by omega. Similarly, we have vertex covering set. So it's a subset of this vertex set, so that every edge of G is incident to at least one vertex. Similarly, the cardinality is vertex covering number. It's denoted by tau. So we have two graph parameters, omega and tau, which will be used in further discussion. So use these two parameters in getting this SKG. So here it's in terms of omega, and then Das, Mojalal, and Gutmann in 2015 found SKG in terms of tau. You see, the right hand side, M is there, but tau is also there. We need to remove this tau. Here, you see M is there and omega is there. Again, we need to remove this omega. Now let's come to more information about this conjecture. If sigma is the number of Laplacian eigenvalues greater than or equal to 2m by n, this 2m by n is the average degree. So we are replacing k by certain number. Now this k is like here in this case, we take this as the average degree, that's in terms of sigma. And in 2015, we were able to find this S sigma G, that is the sum of sigma greatest Laplacian eigenvalues here. We were able to get this bound, and it appeared in 2015. And we were able to verify this Brouwer's conjecture for large families of graphs given by gamma 1 for these families of graphs. And then in 2016, we verified in terms of the clique number and the covering number, we obtained this stronger bound, that's SKG, was in terms of tau and omega. So two are together appearing here. Imagine in the earlier two bounds, one was in terms of tau, one was in terms of omega, but here these two jointly appear in this bound, and we were able to verify Brouwer's conjecture here. You can see now Brouwer's conjecture is true for all graphs belonging to gamma 1. Similarly, we define another family of graphs by gamma 2, and they will look like this figure, a graph of this gamma 2. And we have proved that the Brouwer's conjecture is true for these types of graphs also. And then gamma 3 look like this, where we have a bipartite graph here, complete bipartite graph, and it has some graphs attached to it. It is a cycle here, it's a cycle here, and all other vertices are pendant vertices. So we have verified Brouwer's conjecture for the large classes of graphs belong to the family of gamma 1, gamma 2, and gamma 3. And further, we were able to prove this conjecture for graphs belong to this family. This family is denoted by, here we can say G, such that G is a graph of order n with. So imagine a graph where the clique number is connected to the vertex covering number by this relation. Omega is equal to tau plus 1. All those graphs put in one family, which means every such graph, Brouwer's conjecture holds, whose order is n, and where omega is equal to tau plus 1. Last year in 2019, we were able to obtain further bounds for SKG, and we obtain the Brouwer's conjecture here. You can see SKG is smaller or equal to M plus only one parameter here. This is K choose 2 and this is M. And in 2020, we again proved this Brouwer's conjecture for two large families. One of the family of graphs is obtained from the clique size omega by identifying each of its vertices to a vertex of an arbitrary C cyclic graph. And the second family is composed of the graphs in which the removal of the edges of the largest complete bipartite subgraph gives a graph where non-trivial components are C-cyclic graphs. So this was in this year itself to verify. This is the first family. The first family, it's here, and the second family is here. So again, further development for this Brouwer's conjecture. So we proved this SKG to be true for these types of graphs here. It's just to appear. Okay, so this is the development of about Brouwer's conjecture. So in general, it has not been settled. This Brouwer's conjecture problem is still open. And we go to one more concept. I will see how many minutes I have. Well, I have 10 more minutes, so I can go further. So I discussed earlier about signless Laplacian matrix. So in the Laplacian matrix, it was minus here. Note this here, it was minus here. Now it's plus. So the matrix defined by diagonal matrix, this degree matrix plus the adjacency matrix is QG, which is called as signless Laplacian matrix. Spectrum is signless Laplacian spectrum or Q spectrum. It's again real symmetric, positive, definite, and we denote the signless Laplacian eigenvalues by Q. So lambda are related to the adjacency matrix, mu is related to the Laplacian matrix, and Q is related to the signless Laplacian matrix. In case we denote the k largest signless Laplacian eigenvalue, see we have put plus here, means it's for signless Laplacian by summation of qi. Then there was a conjecture similar to Brouwer's conjecture. So motivated by the definition of SKG, the following conjecture was put forward. This is the conjecture. Again, it's in terms of only one parameter. This conjecture came in 2013. And there is some progress about this conjecture. It has been verified for certain families of graphs. You can see for k equal to 1, it's true, k equal to n. This is a similar type of conjecture like Brouwer's conjecture, but verifying this conjecture at certain stages takes a different direction and needs different techniques to obtain the validity of the conjecture. So the contribution for this conjecture, Ashraf itself, in 2013 verified for graphs when k is equal to 2 and for regular graphs, and then Yang in 2012 also verified this conjecture for certain families of graphs. Here it is in terms of vertex covering number, and in 2019 we were able to obtain bounds for upper bound for SKG. This is plus here. And it was in terms of clique number omega, and this is in terms of diameter d, and we verified the conjecture for several families of graphs. And in 2012, we did some more work on this signless Laplacian eigenvalues conjecture, and we proved that this conjecture B, which is signless Laplacian conjecture, is true for many families of graphs. This conjecture is also still open. So now there are two, they make up two conjectures. One is Brouwer's conjecture, one is signless Laplacian conjectures. Both are open. Now I will go to the extension of this problem. Now we define this transmission of a vertex as the sum of the distances to all other vertices. Like here you see the transmission of a vertex is defined by this relation, and the graph is R transmission regular if every such is R, and the transmission of graph is denoted by sigma G, and sigma G is 1/2 of this all transmission. And the distance matrix is defined by dg. I said earlier that distance matrix is defined when the entries are the distances, and then we have the second transmission, and we have the diagonal matrix. Ashish and Hansen introduced Laplacian and signless Laplacian matrix for the distance matrix. So this was distance matrix. Now we have Laplacian distance matrix and signless Laplacian distance matrix. So these two matrices, this is distance matrix, this is Laplacian distance matrix. It is the transmission minus the matrix dg. And if we take, instead of minus, we take plus, it becomes this matrix. So this was introduced by Ashish and Hansen. And if G is connected, then this Q, dQg, I will focus on this dQg is symmetric, non-negative, and irreducible. The eigenvalues are taken in the non-increasing order. And we have the third problem, which is denoted by C. For any connected graph G, which is not a path, this mkg is less or equal to sigma g plus k plus 2 choose 3. This is true for k equal to n minus 1. We have proved it for k equal to n. It's true for g not equal to the paths. It's true for kn. It's true for connected threshold graphs of order n bigger or equal to 19, very big graphs. And it's true for graphs with diameter 1 and diameter 2. It's true for separate graphs. And we have proposed the following conjecture. This is conjecture D. So my co-authors are here. So we have put forward this conjecture, and this conjecture, along with the development of this conjecture and related problems, can be found in linear and multilinear algebra. The DOI number is here. So it's online now, and the conjecture is again unsettled. So this is an analogous conjecture for distance matrix, for distance signless Laplacian matrix. Analogous conjecture of the Brouwer's conjecture, but here you can see the conjecture is somewhat in a different form. So m is not there, but n is now here. You see n is involved, the order of the graph. Now what supports our conjecture is the following. It's true for graphs of diameter 1 and 2. It's true for threshold graphs and complete split graphs. It's true for graphs with k equal to n minus 1 and n. But conjecture D is still open. Okay, so I think my time is over, or still I have a couple of minutes. So Laplacian energy, I'll stop here because I think it's now. Okay, let's define this Laplacian energy. So this is analogous to the energy of graphs. We define the Laplacian energy. It's equal to mu I minus 2i m, where this is the average degree, 2m by n. And we say that there are certain problems in this Laplacian energy which can be settled if the Brouwer's conjecture is settled. So there are certain problems, very interesting problems in this Laplacian energy and distance Laplacian energy, which are still unsolved, but their solution can be taken from once we have a progress on the Brouwer's conjecture, which in other words means that if Brouwer's conjecture is settled, we can have the progress, we can have some breakthrough in these problems also. And I think so I should stop here, and thanks for your attention. If you have any questions or comments, I'll be happy to answer those comments and questions.
Any doubt from audience? Any doubt? Very nice lecture, sir. We thank very nice lecture on Laplace hygiene.
Students who will come for vote of thanks, ma?
Students have
Session
any doubt?
conclusion and vote of thanks for all
Otherwise,
session.
we close this section.
No, sir. Students will come, sir.
Any doubt, not question. Any doubt, please clarify.
Hello, ma. Professor, I am Dr. Bhuvaneshwari.
Thanks, madam.
No, sir. Students will come, sir. They are well prepared and they are waiting for our invitation, sir. Professor, I am really more happy with us in this session.
Waiting. If you want, you ask doubt. Otherwise, we.
Vimala, who will come for the session conclusion, ma?
Sir, Sharmila. Sharmila, ma'am.
Sharmila.
Yeah. Gratitude is one of the least articulate of the emotions, especially when it is deep. I would like to thank our honorable speaker, Dr. Espizada sir, for visiting and enlightening us with knowledge. Today's lecture was full of informative and experimenting things. It gave deep insights into the topic. I really enjoyed when you gave us a deep knowledge about the applications and the basic types of matrices, especially adjacency matrix and diagonal matrix. It's a new topic for us about Laplacian matrix, energy, and spectrum. But it doesn't seem to be any other hot because of you, sir. Thanks a lot, sir. It is the first time we know about the connection between the diameter of the graph and the number of distinct eigenvalues of graphs. All the theorems presented by you is really understood because of your explanation with your awesome words, sir. It was very nice to hear about crow graph, split graph, threshold graph, and Schur's inequality, Brouwer's conjecture. It will definitely play an important role in our future life, sir. Once again, I would like to deliver my sincere thanks to Dr. Espizada, sir, for taking out time from the busy schedule of your life and enlightening us with knowledge. May this beautiful afternoon fill your heart with happiness. Thank you, sir.
Thank you, Professor.
Thank you very much, Professor.
Professor, one of my students is raising their hand.
Sure, I'm here.
Very nice lecture, sir. I have no doubt, sir. Sole Raju.
Any student, anyone, if he has, they can contact me through email or anytime.
Talk.
Absolutely no problem.
Very good talk, sir. Very nice. From the preliminaries, references.
My pleasure.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, sir.
Can I close this section?
Yes, sir.
Madam?
Sir, why we close? Shall we continue, sir? Because the introduction section will be start. Thereafter, madam will continue. Madam?
Okay, for me, don't want introduction and all. I'll go directly to the
Ma'am,
session.
even though we give a mild introduction about you, madam, as I invite Dr. A. Amaravati, madam, to give a little bit introduction about our HOD, madam. Dr. Amaravati. Dr. Amaravati. Okay. Sir, unmute Giri Aravind name. Is Kannan, sir?
Yes, madam.
Sir. Okay, sir. அவங்க unmute பண்ணாம இருக்காங்க போல இருக்கு.
Amaravati, unmute பண்ணிட்டாங்க.
Okay.
Yeah. Don't want further, ma'am.
Good afternoon to all.
Good afternoon.
Good afternoon to all. Madam, can you hear? Good afternoon to all.
Your voice is fully audible, ma'am. You can proceed.
Okay, madam. On behalf of the organizing committee and participants, I would like to introduce our chief guest, Dr. K. Bhuvaneshwari, Associate Professor and Head of the Department of Mathematics, Mother Teresa Women's University, Kodaikanal. She is an MSc, MPhil, PhD degree holder in mathematics. She got gold medals in the UG and PG degrees with the university first rank. In addition to this, she has also done MCA, MPA, and PGDCA. She has obtained her doctoral degree in the area of fuzzy and digital topology in Bharatiya University, Coimbatore in the year 2000 to 2005. She has published more than 100 research papers in various national and international reputed journals related to her area. And also she has published 5 book chapters in the research field in the national and international level. She has 30 years of academic and industry experience in mathematics with the computer applications and master of computer applications departments. So far, she has completed 55 MSc projects, 51 MPhil and 30 MCA in various colleges and universities. And also she has guiding 20 MSc students, 3 MPhil students in Mother Teresa Women's University, Kodaikanal. She has acted as PhD external member in various colleges. She has attended many refresher courses, FDP and other conferences. She is a director of Swami Vivekananda Higher Studies and Research Center. She has organized various international programs in Mother Teresa Women's University, Kodaikanal. She has also delivered guest lecturer and invited talking in various international and national conferences, seminars and workshops. She has also acted as a chairperson. She has also an chairperson in national and international conference. She has also evaluated 32 PhD theses in various universities and also evaluated MPhil thesis. In addition, she has also acted as a board member, doctoral committee member, inspection member committee, board of studies member, governing body member, Madurai Commerce University vice chancellor nominee, selection committee member, coordinator, computer learning program, NCC coordinator, YRC coordinator. The list is endless. We are very lucky to have such an expert for this webinar with a brief introduction.
Thank you, Amravati. Thanks,
ma'am. Once again, she is a great inspiration to studies and research scholars. And today we have got a golden opportunity to listen to her speech, which would enlighten us in a new dimension. I welcome you, ma'am.
Thank you, Amravati. Thanks for your introduction. Now I'll directly go for the session, sir. Solera, sir, shall we enter into the session, sir? Whether my screen is audible, ma?
Yes, madam. Yes, madam.
Yes, ma'am.
Whether my screen is audible? Yes. I am Dr. K. Bhuvaneshwari. Today I am going to give a lecture in applications of fluid dynamics in medical field. In my MPhil, I did my research in fluid dynamics. Actually, nowadays my research is in topology. In my MPhil, I did my research in fluid dynamics. So there I did a research in fluid dynamics alone. But nowadays I'll think about how to implement my thesis. I did my MPhil in 1991. How to implement that part, how to use that fluid dynamics application in medicine field. Now I'm having an interest in medical field. So I'm interested to implement that thesis part in the medical field. For that, I took the initiation. This is the very good application-oriented paper, fluid dynamics. Generally, fluid means we can't think it is a liquid. It is either a gas or a liquid. Both will come in the fluid dynamics. There, my topic in 1991, I did my research under MPhil under Dr. Anjali Devi. Now she was retired in Bharatiya University. My research topic there is heat transfer, observing heat transfer in a viscous flow, that is a incompressible viscous flow. The flow is between eccentrically rotating porous disc. During the time when we send a flow, that is a liquid, viscous liquid, through the porous disc, and the porous disc is eccentrically rotating, that is, it is rotate itself. During the time when we pour some water, we inject some water or some fluid into that flow, how the heat will transfer, how the flow will disturb. And we suck some water from, using syringe, we suck some water from the flow, how the flow will disturb, how the heat will disturb. Like I was studied 3 parameters, one each case, 2 cases I did. In both the cases, I studied 3 parameters, how the flow will disturb, how the flow increase or decrease, heat transfer, and the molecular change, speed, everything I was studied. So I am thinking to implement that in the medical field. The work is going on now. Even though I never published the paper in this, but I was implementing now. The result is very soon I will publish the paper in it. In this medical field, the going on work. 3 papers I am preparing for that. Now I will get some idea about graph theory as well as fluid dynamics to implement it. Here I'll just give an introduction about what is fluid. Fluid means, I already told, don't think fluid means it is a liquid alone, it may be a gas. For example, a column of smoke rises from a campfire. Why does rising smoke curl, twist? See, in smoke, it comes from a campfire. It comes little bit, and then it has some twist or curl. How, why it comes? That is one question. And another one is water stream from a firehouse. How does a nozzle increase the speed of water emerging from a house? So, as if suppose a water is going on in a pipe, when using nozzle, we are how to increase it, how to decrease it. So for that, what we want to do, what is the relation between? So using these two concepts, I'm going to implement my research in the blood courses through our vein. How does the body regulate blood flow? So for the third question, I will explain, and I'll come back to the implementation of first two question answer into the third part. Blood courses through our vein. So that is example I am giving for the blood fluid flow, fluid dynamics in medical. But in that only our life, our day by day life is going on. Blood flow, they decide everything. Blood flow decide our lifetime, healthy life or whatever may be. So in that, how does the body regulate blood flow? So for that, I'll give some example to you before it. Flow rate. I'll link our general flow with the medical field. So for the first question, I'll come for flow rate and its relation to velocity. Flow rate Q is defined to be, so already I have given I raised two questions. Why does rising smoke curl and twist? How does the nozzle increase the speed of water emerging from the hose? So for these two, flow rate and its relation to velocity. So how to decide the flow rate? How to relate this with the velocity? Flow rate Q is defined to be the volume of fluid passing. Remember that flow rate is defined to be volume of fluid, how much fluid passing by some location. Since the fluid is flow through the three-dimensional figure, so I'll take the volume there. So how to find the volume? Again, I'll come back. Passing some location through an area during a period of time. So here we are using a cross section of area is more important, and its velocity is also more important, and the period of time. So I won't link all the three. Flow rate is the volume of fluid per unit time flowing past a point through a cross area. So area I'm taking as A, and the flow rate is Q. Here the shaded cylindrical part, this part, shaded cylindrical part, a point through a area A. Here the shaded cylindrical part, the fluid flow past a point P, here the point P, in a uniform pipe in time T. So I'm taken the time as T, the cross section area as A. Therefore, the volume of the cylinder is AD. Volume of the cylinder is cross section into the diameter, and the average velocity V bar equal to distance, that is a D by T, so that the flow rate Q equal to AD by T, or that is equal to A into the D by T is nothing but V bar, so that we defined here. So we are having an idea about how to find flow rate, normal fluid, how to find flow rate using the cross section of a pipe, everything. Now I'll come for the third slide. How does the blood circulatory system work? Here we were discussed about how the fluid flow through a cross section area A at a unit time T in a particular point P. We were discussed using this application. We will discuss about, and this is an initiation of fluid flow. And again, I will discuss about how does the blood circulatory system work, and then we can implement these two concepts. We will get more information. We will give more information mathematically to the biology people. Mathematicians we are the person to give an exact solution. And again, I already used to discuss with our colleagues, mathematician don't want any laboratory, don't want any nature support, don't want any instrument support, don't want any chemical combination support. With a pen and paper, we can able to sit in a ideal room and we can give solution to entire world problem. That's why I always used to tell in my talk, conclusion never ends when marks get denied. When we planned to organize this conference, we were myself and Dr. Solera sir and Dr. Vimala madam were discussed about to finalize the topic, and we most of the speakers are in graph theory, but we give an applied mathematics. The topic is in applied mathematics, since mathematical application is a point, it is a supporting aid. Without the application of mathematics, as our Vice Chancellor Madam in her residential address morning Madam told, without mathematics, and our Registrar Madam also quoted some examples, without that application, without our mathematical aid, nothing will conclude in the world, day by day problem. That's why we are thinking to implement that. Now the current scenario is a medical field and biological field. They need support from a mathematical part. Even in a petroleum engineering research in IIT and somewhere, I had a discussion with one professor in petroleum engineering research people, and what he told, no, madam, we were developed only the model of differential equation, PD and ODE, for our petroleum engineering and somewhat another problem, but we don't know how to solve it. We can give a conclusion, but we are expecting your support. So the differential equation application, numerical method application, and our what the fluid dynamics application will show. Numerical method is applicable in all civil, mechanical, and every area. Differential equation in solving, wherever we have a change there and all, we use for a differential equation. And the fluid dynamics application will come for industries, fluid usage places, wherever may be it, particularly in a biomedical. That is more important. Now we will discuss about biomathematics. Instead of saying it is a fluid dynamics, I can say it is a biomathematics, since we are using not only fluid dynamics here, we are going to use a differential equation as well as a graph theory approach also for the conclusion. So it is a biomathematical part in the blood system and our human body analysis. The blood circulatory system, that is vascular system, deliver nutrients and oxygen to all cells in the body. I already told it is a biomathematics. That's why here in a cells, see, remember already 2 sessions were over in graph theory. A graph theory person also can interact, can support, can talk, and about this part. And I'm expecting graph theory person also will collaborate with me for this research. It consists of heart and the blood vessels running through the entire body. So the circulatory system, it consists of the heart and the blood vessels running through the entire body. The arteries carries blood away from the heart. The vein carry it back to the heart. So there are 2 type of blood vessels in our human bodies. So one is it takes arteries carry blood away from the heart. That whenever heart pumping, it takes oxygen and nutrients to the entire cells. And another one is through vein, again the blood will go into the heart. The trunk, the main artery, branches into large arteries, which lead to a smaller and smaller vessels. The smallest arteries end in a network of tiny vessels known as the capillary network. Now, I will discuss about blood vessels again. Blood vessels are the network of pathways through which blood travel throughout the body. So in don't want to divide that. Because of the blood vessel, we can able to send the message. So here the blood vessel is the tube or the instrument, whatever may be, it carries the blood, whether from the heart to cells or from the part to the heart, whatever may be it. Here, arteries are the blood vessels that transport oxygenated blood from the heart to various parts of the body. They are thick. So what are the type? What is nature? They are thick, elastic, and are divided into a small network of blood vessels called capillaries. So it part also, there also we are using network. So whenever we are thinking about network from one part to another part, one section, see, the veins are not in the same thickness. It may be varying from place to place. So the changes come from the part to there. We may take it as a notes and we can conclude, we can come for the application of graph theory here also. The only exception to this is the pulmonary articles, that is from the lungs part, that which carries deoxygenated blood to the lungs. And what about veins? Veins are blood vessels. Again, it is one part of vessel, blood vessel that carry deoxygenated blood towards the heart from various parts of the body, from the various parts. So in our hand, in our leg, whatever may be, we are having two type of blood vessel. One is arteries and another one is veins. Veins are from our body to heart, and that is arteries are from the heart to the. So there are two types. They are thin, elastic, and are present close to the surface of the skin. So the veins are very close to the surface of the skin, and another part, that one is that is interior. Veins are in the outer part. However, pulmonary and umbilical veins are the only veins that carry oxygenated blood in the entire body. Anyway, we have an idea about, see, we are going to think about the how the fluid flow. Already I told about my topic. I want to observe heat transfer, and based on the heat transfer, how come we are using differential equation application, and based on the that change, for that I am using differential equation, and flow rate and everything. For that we are using some graph theory application also here. Now the velocity of the blood flow. Just I gave an introduction about what is flow, how to find an velocity, what is the relation between velocity and circle, that is a cross section area, everything in the first slide. In the second slide, I was discussed about how the physical body and how blood flow in our body from heart to the part or part to the heart, whatever may be. Now we will discuss about velocity. I am combining those two in the third slide. Velocity of blood flow. Blood flow is a pulse wave that move out from the aorta and through the arterial branches, then is reflected back to the heart. So blood flow, before it I want to discuss about an important thing. That is viscosity. I use only viscous flow. Our blood is a viscous flow. When I'm pouring some ball or some iron ball, whatever may be that into an ordinary water, means it will go down easily. I'm having two tumblers. In one tumbler I'm having a that is water, and another one I'm having an oil, and that thick that is a density oil in another tumbler. And when I'm pouring a ball into the tumbler which has a water, means the ball will reach the bottom easily. And when I pour a ball into the oil, that is a thick density oil, mean it takes little bit time to reach the bottom of the oil part. That means what? I am pouring both the ball in the same speed, but the viscosity, that is the viscosity will reduce the speed of the flow. So like when I'm in, I'll come for that conclusion, then only you can discuss. Now flow is the movement of liquid or a gas over a time. Flow means, here I'm giving an example. Flow can be calculated by multiplying velocity, comma, the distance moved by an object over a time with a cross-sectional area. Remember that flow can be calculated by multiplying velocity, comma, the distance moved by an object over a time with a cross-sectional area within the circulatory system. Since our body is a circulatory system, it is a connected graph. Velocity can be altered by a change in blood pressure, vessel resistance, and blood viscosity. Now I am thinking about viscosity. So we will think change in blood pressure. Velocity can be altered by one. Already I told, when I am pouring a ball in a tumbler, both in one in that is water and another one in oil. The ball will go a little bit earlier than the ball in the liquid, that is oil. So the pressure, the velocity within the circulatory system, the velocity can be altered by, velocity will decide. Already both are in the same velocity, but because of viscosity and the second one go little bit time taken. So velocity can be altered by change in blood pressure, vessel resistance. So the resistance of the vessel is also more important, and blood viscosity. Blood vessels can vasculitic and vasodilate, which alter cross-section area. That is more important. That is vessel resistance will come in that part. These various factors are under tight regulation to maintain sufficient blood flow to the body's organ and its tissues. So remember that I won't decide already in a velocity of the flow in a normal pipe means we will decide about the distance, time taken, cross section, everything. But in the blood flow, additional point also we should remember in our mind. One is a blood pressure and another one is a vessel resistance and another one is the blood viscosity. So based on these things, we will decide the velocity of the blood, that means in the circulatory system. These various factors are under tight regulation to maintain sufficient blood flow to the body organs and tissues. The flow of blood around the circulatory system is modulated by numerous interacting factors. That is, what are the things? The science dedicated to understanding this flow is called hemodynamics. I already told. We can come for biomathematics. Biomathematics in the sense we are using our mathematical concept, mathematical tools. What are the mathematical tools we use to solve our biological problem means we can easily particular partial differential equation will come under the title of biomathematics. I'm sure. Since for biological development, whether it is an animal biology or plant biology, whatever comes, the rate of change in the growth, rate of change in the tree or in an animal body or tissues, whatever may be it, there may be more than one independent variable there. There may be more than one independent that is points are there to stimulate their growth. So those independent stimulating organs or stimulating items, or we are using it as an independent variable. And for a particular item, how the change will, how the growth will come, for that in a biology, we are using partial differential equation to predict with our data, with our existing data, with our practical experience. And with the future climatic condition or the concept, whatever may be it, we are using here to predict what will be the growth, what will be the destroyable part, and how it will destroy. So like that, the change to decide the rate of change, wherever we are having an undeterministic situation, there and all we need a aid, mathematical aid to predict what will next and what happened in 10 years before. Like that, we are using here. So in that situation, I already told our uh, webinar is covered 3 topics. One is a numerical also, fluid dynamics, graph theory, and in biomedical, we are using here the partial differential equation is also supporting us. And in numerical analysis, we are having an interpolation and extrapolation. So that also can be used for the missing values and the growth rate for a particular X, what will be Y, like that. So mathematics is a aid, I already told. Without mathematics, no one will conclude their part. And here, the part we are studying, the science dedicated to understanding this flow is called, that is a blood velocity of the blood or blood flow. That is a particularly we call that field as a hemodynamics. So when we go for a hemodynamics, we can study about how the human bodies or any blood vessels, how it works. So when we go for hemodynamics instead of fluid dynamics, they are channelizing that from the fluid dynamics. They are particularly channelizing study about blood flow, that is called hemodynamics. So the word itself, we understood that how the fluid part move the blood, particularly they are channelized to the blood. So instead of fluid dynamics, they call it as a hemodynamics. Velocity and pressure. I already told here the velocity of the blood is depending upon the blood pressure also. So how we relate velocity and pressure here. Movement of blood throughout the circulatory system. Again, I am telling circulatory system. So we can come for a graph theory approach also here. And depending upon the size of the vein, you may ask how, madam, it is possible. I am telling that we were discussed about already weighted graph also. Depending upon the vein, the cross section, we may give weight for the cross section as the weight of the particular edge. From one part to one junction to in our body, from our one junction to another junction, the vein, that part, so how it will. And so like that, the weight we may assign and we may give an important for the blood flow. We may study for the blood flow using this concept. Movement of blood throughout the circulatory system is created by differences in pressure generated by the pumping of heart. So movement of blood throughout the circulatory system is created by differences in pressure generated. So how the pressure will generate? Because of the heart pumping. So generated by the pumping of heart. Pressure is greatest immediately after existing the heart and drop as it circulate around the body. So nearer to heart, the pressure is after existing the heart, it is the greatest, and the rate will slowly decrease, slowly drop as it circulates around the body, particularly through the arteries and a capillary network. So in that network, capillary is the very lowest part there. The pressure may be very low here. Because we may conclude this using the cross section and weighted graph concept also here. A greater difference in pressure result in a greater velocity, assuming all else remain equal. So when increased blood flow is required, the heart can pump more quickly and also in larger volume. Velocity and resistance. Here we were discussed about velocity and pressure. Here the velocity and resistance. Velocity and resistance. What is resistance? Resistance is the force that must be overcome by pressure in order to flow to occur, and is a factor of vessel length. Again, I'll come for here this part. Vessel length. diametric surface composition, and the viscosity of the liquid flowing through. So based on this, we can decide about the resistancy. As resistancy increases, the differences in the pressure which influence velocity decreases. Resistancy, sustainability. Resistancy means it pulling down the pressure. If it has more resistancy means automatically it pull down the pressure and the flow will get, the flow speed will get decreased. As resistancy increases, the difference in pressure which influences velocity decreases, which in turn reduces flow. The narrow arteries rapidly reduce local blood pressure and slow the flow of blood through the capillaries, a beneficial effect allowing for the efficient transfer of the chemical and nutrient. Here I will come for one part. And what is the study? In one part, in for a medicine, suppose we are having some physical problem, headache or fever, somewhat we are approaching doctors, physician, and they will give two type of treatment for us, two type of treatment to our body. Either they will give a tablet, and the from the stomach we can take it through, and it absorb easily to our stomach part, and it will that is mingle with that one body. That is one part. And another one is they will give an injection, and through injection, the injection is to vein. Remember that already we are familiar. Vein is nearer to the skin, and the vein is the one of the blood vessel. It takes blood from our body to the heart, and it enter into the heart, and again the heart will pump that to the particular vein in our hand. Through doctors will give injection and the medicine to control our disease or reduce the pain, whatever may be it. So through vein, here the chemicals and nutrients again it transfer from one part to another part. It reach to the heart, and the heart will pump it, and with an oxygen it pump it to entire body of the our body part. And again that part, that cells will receive it, and the rate of that is relieving from the pain or rate of disease relieving will come due to the part. So how it will take? However, pathological changes in blood vessel that result in narrowing or an increase in surface resistance. One thing you remember, it is an easy one. Medical part is not nothing. Our body, ourselves, we are the good friend. Who is your good friend? Who is your best enemy or biggest enemy means ourselves. My best friend is me to me, myself to me. And who is my worst enemy or best enemy or strongest enemy? Whoever may be, that also me. So our body is the myself is best friend to me. So I can able to study about my body easily. Here I am telling about what one concept is now. I won't think about my body. I won't think about my blood flow. When I'm having it in my mind, I can able to find out the paining part, where it pains, how to move it, how to rectify. It is in our mind part more. 70% we can control our body pain or whatever may be using our mind. Remember that. And the medicines are little bit. It will stimulate. It will reduce the pain only 20%. So mind is more important in this situation. And here pathological change in blood vessel that result in narrowing. Here I am telling, when we are suppose we are having some fever and we are not having an energy, when we approach doctor will give a saline water to our body, that is a glucose, and the nurse will use to tell, please keep your hand straight. Why? When we that is when we close it or we change the direction of the fingers and the hand, means the flow will disturb and the blood will come out from the vein. So to avoid that, so in it what we are thinking about, if the flow path is narrow, means automatically the flow will increase. I think the velocity is the flow is in the smooth path. So what we are expecting now, pressure, velocity, everything will be in a narrow path. It is in the normal mode. Okay, that is our experience, that is our practical view. So in that I can say an increase in surface resistance, and another one is an absorption. When I am pouring a water in a plain surface means the water will go the oily table, an oily wood or a normal with a tiles floor means the water will flow. And I pouring some water in little bit of mud oriented that flow means some part will absorb the resistance, the surface resistance that will absorb some water and the remaining. So when it absorbs the downward means some fluid will go down means automatically the flow, the velocity will decrease. Remember that this is the path and this is the way I'm going to observe, I'm going to implement my research when I'm sucking some fluid, some from the flow, how the heat transfer, how the velocity will affect. So this concept we may use for the medical field and the blood part or injection. I am taking some blood from this part means how to the blood flow will affect. So here can lead to a reduction in pressure, velocity and this flow, which can lead to tissue damage. So the resistancy will play to reduce, it can reduce the blood flow or velocity. Again, velocity and viscosity. Here I say velocity and resistance. Here velocity and suppose the resistance, more resistance pathway means definitely the velocity, the speed will reduce. Similarly, the velocity and viscosity, even though it has a velocity, but the fluid is a viscous fluid means automatically the fluid flow will disturb. And my blood is in one viscosity and I am injecting, I am having some injection, the medicine viscosity is also little bit differ from the blood viscosity definitely. Injection, after the injection, how the blood flow will get changed and how long it will take to in the normal blood from one part to another part, how long time taken transfer a medicine from this part to that part, we can easily say from with the viscosity of the blood and our experience, velocity, pressure, everything we can already predict it. But when I'm injecting, I'm having some injection with the medicine, that medicine viscosity is definitely differ from the blood viscosity. So after injecting that medicine in a particular vein and from one part to another part, how long, how variation will come for the blood flow in earlier comparatively, we can correlate and we will give some suggestion, and based on that we will give a time taken to cure it or time taken to reach that medicine to that particular part. Blood is a complex liquid formed from plasma and containing numerous cell types. As such, its viscosity is changeable depending on osmotic balance and cell load. So viscosity of the blood is also changed from the situation to situation. Increase in viscosity such as reduced water content. So when I'm increasing the viscosity means from the blood, the water content reduced means automatically the viscosity will increase, lead to increase in resistance and thus reducing in flow. Remember that I want to reduce the blood flow. The blood has some viscosity, it flowing in the speed. I plan to reduce, that means I plan to reduce the speed means from that we reduce the water content in the viscosity in a fluid means that when water content reduce mean automatically it comes in the thickness, the density increase or viscosity increase. Increasing the viscosity makes it increase the resistance also, and that is the pulling part. The pulling power also increase, that automatically reduce that reduction in flow. Now we think about vessel area. So these are the things we are having idea about how the pressure and resistance and pressure and viscosity. We were thinking about all those things. Now vessel area. Blood vessels are capable of vasodilation and vasoconstriction to alter the diameter. This is very important. When we are in Kodaikanal, in chill climate, many of them used to tell, when we are in the Kodaikanal, when we having some wound in our body by accident or somewhat, it will not get cured easily as compared to the plain surface. Why it comes means, it is in the chill climate. The chillness makes the blood flow to be, that flow rate will be low compared to our plain surface. So that's why here blood vessels are, there is the diameter also part. Assuming all else remain equal, a reduction in diameter result in a reduction in flow. So diameter length reduced means automatically the flow rate also will get reduction, whereas an increase in vessel diameter result in an increase in flow. So the vessel diameter increased mean automatically the flow will increase. And because of the already I told, my part is a porous disc. It is eccentrically rotating porous disc. Through the disc only, in between those two disc only, flow is going on, and the heat transfer and other parameters are studied using that part. So here we are using, our body is a porous disc. We are having a hole. Porous means it is a micro nano holes in our skin. So because of the skin layer, we are having our skin layer is here porous disc, and here we are studying the blood flow rate is a fluid flow in a vein or that is a blood vessels in both the way. These individual elements are, that is a regulation, are tightly regulated by the body to maintain sufficient flow to the body organs and tissues. Now, local regulation of blood flow. Blood flow is regulated locally in the these capacities by using some that is exercise. Regulation of blood flow is managed by adjusting the contraction or relaxation of smooth muscles fiber in the walls of arterioles, and that is in the blood vessel we are using some exercise, and when the exercise makes it the flow is in the normal pathway. That is more important, that is the point. And control can be that is systematically we can do, and the circulatory system will affect, or we can change the flow using some exercise. That is the part. Blood flow in skeletal muscles. The blood flow to an active muscle changes depending on exercise intensity and contraction frequencies and rate. Many things will come. So the skeleton muscles, when we here, it is more important. The circulatory system is closely associated with the skeletal muscles, and to provide it is that is when an oxygen transformation, whatever may be it, when we are doing some exercise, walking, everything, our automatic, the skin is a porous disc, it transfers some unwanted things to outside. So unwanted, that is a heat to the body, that body heat will reduce the that is a resistancy, and it will increase the blood pressure and movement of this part. So that is more important. So we are having a demo for that is an exercise part also. So these are the concept. Here we are having one example, that is a one diagram. Since I am nearer to my conclusion part, so I'll explain this part and correlate my research work in that. This is a skeletal muscles, that is a skeletal muscles. One is a bone, the number one is in this part is a bone, and two is a perimecium. Here we are having that outer layer is a perimecium, and the small holes are here. We are showing that is a blood vessel, and muscle fiber is that here, and five is a, so here it is a what will come for the blood vessel, that the entire part, what are the things in the cross section, it is given, and we can able to implement. I don't want to explain it further since I will go for my part. Here I'll come for that is a part I'll explain. So in this diagram, if you want, I'll share it. Before it, I'll come for the since only 9 more minutes for me. So I won't tell about what is application of fluid dynamics in medical field. Particularly, I am thinking about what is incompressible flow, what is compressible flow, and then only I can able to say in an incompressible flow, viscous flow, I can fit my research with this body. In incompressible flow means what? In this fluid, the density of the flowing fluid is constant during the process of flow. Whatever may be the flow, the density is same. It is not varying from the place to place. One thing you remember, already we were discussed about the blood. The blood viscosity is changing from the part to part. So our blood is not incompressible. In this fluid, the density of the flowing fluid is constant during the flow, means it is called an incompressible. Compressible flow in this fluid, the density of fluid does not remain constant during the process of flow. In other words, the density of the fluid changes from point to point in compressible flow. So we can change in a weighted graph also. The weight of the edge is always change from one node to another. One edge is one weight, and from the same edge only continuing in a path. But from the second node to third node, its weight is changed. So like that we can use it and we can classify that. So compressible fluid means in that part viscosity is changing. So our blood is compressible here. It is not an incompressible part. So with the definition of what is meant by incompressible, that is a density is change. Constant means is it incompressible. Compressible means density is remain. It is not constant. It varying means it is called compressible. So in a compressible fluid, here we are now. I will come for the conclusion part. Study of we are using study of heat transfer in an compressible viscous flow. My study is in compressible. In an one is an incompressible. Here I cannot use. It is in a compressible viscous flow through eccentrically rotating porous disc. So I fit to that part. I take the same result. I'll come for the medical field. I can apply my part, the case studies, whatever may be the results, and then an equation. Up to the development of equation is one and the same. I can change little bit and I can implement it, means automatically we can give a solution in a medical field. One thing, when we go for a hospital, in many hospital I saw that, and doctor is giving treatment, and God is the deciding authority whether we are going to live in the world or not. Doctor is not. All the doctors are not a God. They are giving treatment. They are in between. They are bridge between us and the God. They are believing that, but they are writing and they are showing it in the hospital. But their belief is they are the God to predict our life. Not like that. They may predict, they may save our life with their medicines. But one thing, when it works, which time it will recover, that we will decide based on our muscles, based on our resistance capacity, based on our body absorption capacity, medical, that is a chemical absorption capacity in our stomach or in our vein to transfer that medicine, resistance power, everything. We can say, if it is a simple word in a COVID-19 time also, many of them are discussed. If they are having, and that is we are having resistance power. We are having that power means we will escape from the disease. How we are having resistance power in our body, we are having resistance power means that chemical or that unwanted molecules will not pass through our blood. Since our body has a more resistance, it absorbs the unwanted thing and it will not allow that unwanted bacteria or something to mingle with our blood and flow through the body part. That's why they are telling you are having more resistance capacity. That's why your stamina, you are having more stamina to balance all those things. Yes, it is true. So how to improve that? In which part we are having more resistance? So everything we will think, we will predict, we will give an information about with the help of our mathematics. Change in heat and flow. Flow means flow rate. When fluid is injected through the flow. So when automatically a body flow is going on here, and doctors used to inject some medicines, viscous, more viscous comparatively. Medicines is a little bit more viscosity, that how the flow will get changed. So these two are my studies, and using the fluid dynamics, entirely the fluid dynamics, that is called I studied in fluid dynamics concept, and in future we are applying our fluid dynamics into medical field, particularly in a blood flow, that is called hemodynamics. So origin is fluid dynamics. The fluid dynamics, when we convert that fluid dynamics in the flow, that liquid, that fluid is, instead of a normal fluid, we are using here blood means, and that instrument, the flow transfer is our body means, we can come for our hemodynamics part. Our hemodynamics totally, entirely, that hemodynamics mathematically, see, very simple concept, how the blood flow from our body, everything, that introduction I gave, and fluid dynamics already familiar to us. Compare those two and apply some theoretical concept and observations from the doctor's result, everything, and we can come for the conclusion, that is called hemodynamics. So hemodynamics, in this situation my time is over. So hemodynamics support us, help us to give a solution, analytical description of the motion of a continuous viscous compressible media is based on the conservation of mass, movement, energy, whatever maybe we can say. So that is more important. Hemodynamics is the application of, it is more application of hemodynamics part, is more application for a fluid dynamics concept into our human body. Is there any queries and doubt, ma? Is there any queries, pa? Is there any doubt in my speech?
Good.
2 more minutes. Nobody's in the group. Student, please.
Ma'am, is applicable in genetic algorithm, ma'am?
In genetic?
Is applicable in genetic algorithm, that is non-linear optimization approach?
Yeah, we can use that, ma. We can use that. We can use
Okay,
that. I never think about that. Just I used only in the hemodynamics part.
Okay,
And
ma'am.
you may go for that part also, ma.
Okay, ma'am. Okay.
Now
Thank
the
you.
work is going on in the research, ma. So it
Okay,
is.
ma'am.
You can use the graph theory, weighted graph concept, and another thing also here. Particularly, we are using that fluid dynamics concept in a hemodynamics part. That is more important. What we are going to predict.
Predict. Okay. Okay.
Anybody's ma? Shall we conclude the session?
Yes,
One more
madam.
minute. Sir, Professor?
No problem, madam. Finish பண்ணிக்கலாம். நல்லா இருந்துச்சு.
Nice presentation, ma'am.
Nice presentation.
Rumila ma'am, shall we conclude? Organizing secretaries?
What up, thanks. What up, thanks, madam.
Sharmila?
I would like to thank our honorable speaker, Dr. K. Bhuvneshwari ma'am, for visiting and enlightening us with knowledge. From the topic itself, I really enjoyed, ma'am. Application of fluid dynamics in the medical field, it seems to be very interesting. When you have started the session, we are fully drowned into the topic, ma'am. It is very easy to understand when you give examples for each and every topic. The blood flow through our veins is compared to the fluid dynamics was mind-blowing, ma'am. Apart from mathematics, today we have a chance to know some information about our blood circulating system, arteries and veins. It is a little bit exciting when I hear about hemodynamics, ma'am. The definitions about compressible flow, incompressible flow, viscous flow are very clear and well said by your ma'am. Once again, I would like to deliver my sincere thanks to Dr. K. Bhuvneshwari ma'am for taking out time from the busy schedule of your life and enlightening us, ma'am. Mathematics gives us the hope that every problem has a solution. Like that, today we are having an overall vote of thanks. So I would like to request Ms. Hess Emalata to deliver her vote of thanks for our first day's session in 3 days of international webinar on applied mathematics organized by our Department of Mathematics, Mother Teresa Women's University, Kodaikanal.
Student, please, participant, please unmute your camera.
Shall I start, ma'am?
Yes.
Gratitude is one of the least articulate of the emotion, especially when it is deep. Good evening, everyone. I am Hemalata, MSc Mathematics from Mother Teresa Women's University, Kodaikanal. It is an honor for me to have the opportunity to give a vote of thanks on this special day. So we have reached the end of this today's session. First of all, I would like to thank Almighty God for making today's webinar a great success. I would like to thank our Honorable Vice Chancellor, Dr. Vaidegi Vijay.
Your voice is not audible, ma. Hemalata.
Yes, ma'am.
Voice is not audible, Hemalata.
Now, ma'am.
Yeah, it is audible, little bit. Okay.
Shall I start in the first?
Yeah, we start from the first, ma'am.
Okay, ma'am. Gratitude is one of the least articulate of the emotion, especially when it is deep. Good evening, everyone. I am Hemalata, MSc Mathematics from Mother Teresa Women's University, Kodaikanal. It is an honor for me to have the opportunity to give a vote of thanks on the special day. So we have reached the end of this today's session. First of all, I would like to thank Almighty God for making today's webinar a great success. I would like to thank our Honorable Vice Chancellor, Dr. Vaidegi Ma'am, Mother Teresa Women's University, Kodaikanal, and our respected Registrar Ma'am, Dr. C. Hilda Devi, Mother Teresa Women's University, Kodaikanal, and our respected Dr. K. Bhuvaneshwari, Associate Professor and Head Department of Mathematics, Mother Teresa Women's University, Kodaikanal, and faculty members, Department of Mathematics, Mother Teresa Women's University, and Dr. A. Solai Raju, Associate Professor, Department of Mathematics, Jamal Muhammad College, Tiruchirappalli, for creating a wonderful webinar that will benefit everyone. Now, I would like to thank our speaker, Dr. Rajesh, Assistant Professor, Department of Mathematics, Ramanujan College, University of Delhi, and Dr. S. Prisada, Professor, Department of Mathematics, University of Kashmir, and Dr. K. Bhuvaneshwari, Associate Professor and Head Department of Mathematics, Mother Teresa Women's University, for inspiring free speech from a great graph theory and application of fluid dynamics in medical field. I am sure the participants will have a lot to take away from the speech. We are all inspired by your great words. A very hearty vote of thanks to all the speakers for taking time from your respective schedules to grace this webinar. And I would like to thank all the participants for being a great support. Once again, I want to state that we are all most grateful to you all. We thank you for you being with us this evening. It has been a great pleasure. Thank you very much.
Thank you, Ms. Hemalata. Once again, I thank you all. Heartfelt congratulations to the organizing team and the volunteers for your hard work, which has made this function a memorable one for all of us. Thank you to all of you for working closely to mark this function with success. The only way to learn mathematics is to do mathematics. Have a good day.
Sir, session conclude பண்ணிடலாம்ங்க sir.
ஆமா மேடம், முடிஞ்சு. நாளைக்கு ஸ்டார்ட் பண்ணிக்கலாம்.
நாளைக்கு பார்த்துக்கலாம். Thank you very much, sir. Thank you for all your support. Thank you very much. Shall we leave from the session, sir? Okay.
Yes, madam. கண்ணன் சார்.
Yes, sir. Sir.
இது வரைக்கும் உள்ளத ரெக்கார்ட் பண்ணிக்கோங்க.
Sure, sir. Yes, sir. செஷன் க்ளோஸ் பண்ணிடலாம்.
வேண்டாத எடுத்துக்கோங்க, வேணுங்கத வச்சுக்கோங்க.
Yes, sir. செஷனை க்ளோஸ் பண்ணிடலாம் சார்.
ஆமாங்க சார்.
Yes, sir. Thank you, sir. Thank you, sir.
Thank you. Thanks.